Our world is full of roads that shouldn't even be possible. From bridges that cross waters for hundreds of miles, to tunnels that cut through mountains at altitudes higher than we've ever built before. Today, we will show you the most unbelievable roads on Earth and discover how they've been constructed, facing the hardest engineering challenges in road history.
A few engineering feats that match the complexity and precision required to lift a functioning roadway within an existing bridge arch, all while keeping maritime and vehicular traffic moving. The Bayonne Bridge, Raise the Roadway project was exactly that kind of endeavor, a surgical transformation of a legacy structure to meet the demands of modern commerce. Originally opened in 1931, the Steel Arch Bridge connecting Bayonne, New Jersey to Staten Island, New York had a vertical clearance insufficient for newer Panamax and post-Panamax container ships to pass beneath. Rather than demolish and rebuild, the project team pursued an extraordinary solution. Raise the roadway from its original elevation to a new, higher level, without altering the historic arch. The operation began with extensive structural assessments of the existing steel arch, whose riveted trusses were still in remarkably good condition. The original roadway deck hung from vertical suspender cables connected to the arch's underside. These suspender cables were gradually unloaded as crews prepared for the insertion of an entirely new deck system, this time supported above the old roadway and suspended higher within the arch span. Construction began with the fabrication of steel support columns and crossbeams anchored to the existing arch ribs. These temporary and permanent steel components were staged off-site and moved into place with extreme logistical care, as space was limited and much of the work had to be performed from barges or scaffolding. A critical step involved the staged demolition of sections of the original roadway, which were removed incrementally while traffic continued on other lanes. The demolition had to avoid disturbing the live structural behavior of the arch, meaning that counterweights, temporary supports, and load redistribution were all carefully engineered for each phase. After the initial segments were cleared, the new roadway deck segments were installed section by section, elevated well above the original deck level. These new segments utilized orthotropic steel panels with welded ribs to minimize weight while maximizing stiffness, allowing for long spans between vertical supports. To complete the transition, the team had to construct new approach ramps on both sides of the river that gradually transitioned from the existing ground level to the newly elevated bridge deck. These approaches were supported by drilled shaft foundations and used cast-in-place concrete piers and precast girders. Each piece had to align precisely with the central span deck geometry to maintain smooth grade transitions and proper drainage slopes. One of the most impressive features of this project was the uninterrupted use of the bridge throughout much of the work. A movable, temporary trestle system allowed traffic to continue using the bridge, even as sections of the original deck were removed and replaced. This required careful scheduling, custom staging platforms, and constant monitoring of structural loads to avoid overstressing any part of the arch. Instead of dismantling an aging bridge and replacing it with a new one, engineers tasked with the Bayonne Bridge Raise the Roadway project chose an unprecedented path, building a higher roadway within the existing arch structure, all while keeping traffic flowing and preserving the historic character of the original span. This decision was driven largely by the need to accommodate the larger container ships enabled by the expansion of the Panama Canal. The original vertical clearance of the Bayonne Bridge, which stood at approximately 151 feet above mean high water, was no longer sufficient to support this new class of vessels accessing the Port of Newark and Port Elizabeth. Raising the clearance to nearly 215 feet became a logistical imperative. The existing bridge's steel arch, a landmark engineering structure from the early 20th century, presented both opportunities and limitations. its structural integrity remained excellent, allowing it to be repurposed to support a new, elevated roadway. The challenge was that the original deck hung from vertical suspenders below the arch's apex. To raise the roadway, engineers devised a complex method of constructing a new deck above the original without disrupting either maritime activity below or vehicular activity above more than absolutely necessary. The process began with the construction of a series of temporary support structures within the arch, allowing workers to access both the existing deck and the new construction zone above it. New piers and approach structures were simultaneously being constructed at both ends of the bridge using reinforced concrete columns supported on deep foundations, often drilled shafts socketed into bedrock. These approaches would eventually tie into the new elevated roadway. Once temporary supports were in place, workers began erecting steel framing for the new upper roadway within the arch span. This framing consisted of longitudinal girders and crossbeams bolted and welded into position, followed by installation of orthotropic deck panels. These panels were fabricated off-site and trucked in for precise placement, reducing on-site assembly time and improving quality control. The steel deck design provided a lightweight yet structurally robust solution that minimized additional loading on the arch. Throughout this process, extensive structural analysis was continuously performed to ensure that loads were properly transferred through the original arch structure. Sequencing was essential. As the new deck was installed section by section, old portions of the original deck were removed underneath in a carefully planned reverse progression. Traffic was maintained through the use of temporary roadways and weekend closures scheduled around critical lift and removal operations. Seismic upgrades, drainage improvements, lighting systems, and safety features were all integrated into the new deck, bringing the structure up to modern standards without compromising the visual profile of the historic arch. Once the elevated roadway was fully connected to the new approaches, the bridge could serve modern truck traffic and massive container ships alike, without ever having lost its central role in the region's infrastructure.
Next up, it's time to travel to Turkey. The Osmanghazi Bridge, completed in 2016, is a critical component of the country's infrastructure. The suspension bridge spans the Gulf of Izmit, connecting the town of Gebze and Yalova, and forms a vital part of the Istanbul and Izmir highway. With a total length of 1.7 miles and a main span of 5,472 feet, it is one of the longest suspension bridges in the world. Constructing the Osmanghazi Bridge posed numerous engineering challenges, primarily due to its location over the seismically active Gulf of Izmit. To address these challenges, engineers employed state-of-the-art seismic protection measures, including the installation of special bearings and dampers that allow the bridge to absorb and dissipate seismic activity. These features are crucial for ensuring the bridge's stability and safety in the event of an earthquake. The bridge's design includes two massive towers, each rising 837 feet above sea level, constructed using high-strength steel and concrete. These towers support the main cables, which are composed of over 130,000 miles of steel wire, meticulously spun on site to ensure optimal tension and load distribution. The main cables are anchored deep into the bedrock on either side of the gulf, providing a stable foundation for the entire structure. One of the key construction techniques used was the erection of the bridge deck in prefabricated sections. These sections weighed several hundred tons and were transported to the site by barges and lifted into place using specialized cranes. This method allowed for precise alignment and efficient assembly of the bridge deck, minimizing construction time and ensuring high-quality craftsmanship. The Osmanghazi Bridge significantly reduces travel time between Istanbul and Izmir, cutting the journey from 8 hours to just over 3 hours. The improvement has had a profound impact on the regional commerce and tourism, facilitating the efficient movement of goods and people. The bridge also enhances connectivity within Turkey's extensive transportation network, contributing to the country's economic development.
While the next underwater project may not be as big, the Poseidon Underwater Hotel is just as remarkable. This groundbreaking project, aiming to be nestled in the clear turquoise waters of Fiji, extends the frontier of hospitality into the aquatic realm. The hotel is designed to feature 25 suites, each encased in a 70mm thick transparent acrylic shell, providing 360-degree views of the vibrant marine ecosystem. With an estimated construction cost of $105 million, the hotel's ambition is not just to provide luxury, but to pioneer in eco-friendly engineering. The structure is planned to be anchored at a depth of 40 meters below the sea level, covering an area of approximately 5,000 square meters. It's time to visit the United Kingdom, where a tunnel is being constructed for an ambitious purpose. The Thames Tideway Tunnel aims to tackle London's over a century-old sewage system problem. Officially initiated in 2016 with an estimated completion by 2025, this massive undertaking is designed to prevent millions of tons of untreated sewage from entering the Thames River each year. Stretching over 25 kilometers and delving up to 65 meters below the river, the tunnel is a critical component of modernizing London's sewage disposal and treatment capabilities. Costing approximately £4.9 billion, the project is not just an engineering marvel, but also a significant environmental initiative. By intercepting overflow from existing Victorian sewers, the tunnel will ensure that the Thames remains cleaner and more vibrant for future generations. Despite its environmental benefits, the Thames Tideway Tunnel has faced controversy, particularly regarding its financial impact on residents through increased water bills. Let's travel to South Africa for the world's deepest mine. Mponeng Gold Mine in South Africa reaches an astonishing 4 kilometers or 2.5 miles into the Earth's crust. This operational depth exceeds that of any other mining venture globally, including the Tautona mine, which extends 3.9 kilometers underground. Mponeng, which means "look at me" in the local Sotho language, began its operations in 1986 under AngloGold Ashanti and has since become a symbol of extreme engineering challenges. The mine's shafts and tunnels cover an area so extensive that it descends below sea level at points, creating a unique set of geological conditions. To maintain operations at such depths, the mine circulates ice slurry to cool the ambient temperature, which can reach up to 55 degrees Celsius due to geothermal heat from the surrounding rock. Producing over 244,000 ounces of gold annually, Mponeng's output is significant compared to smaller gold mining operations, such as the Porcupine Mine in Canada. The high-grade gold ore body at Mponeng is accessed through a complex network of tunnels and shafts, requiring highly sophisticated drilling and blasting techniques that utilize automated loaders and dump trucks for ore extraction and transportation. Mponeng's vast network of underground development is supported by a workforce of around 5,600 people, each of whom must descend a vertical distance greater than the height of Mount Everest to reach the working faces. The operational complexities of Mponeng extend beyond simple excavation. The mine deals with rock bursts and seismic activity due to the immense pressures at depth. These geological stresses are managed through meticulous seismic monitoring and advanced rock bolting techniques, which reinforce tunnel stability more rigorously than is seen in shallower operations such as the Polkowice-Syracuse mine in Poland. Financially, the development and continuous modernization of Mponeng have seen billions of rand invested over the decades, including substantial sums spent on refining the gold extraction and processing facilities.
At the heart of a massive cross-border logistics corridor between Detroit, Michigan, and Windsor, Ontario, the Gordie Howe International Bridge emerges as one of the most technically ambitious and strategically vital infrastructure projects in North America. Designed as a cable-stayed bridge with an unprecedented main span length for this type of crossing in North America, the structure addresses not only current transportation needs, but also anticipates decades of future commercial and passenger vehicle growth. What sets this project apart is the integration of border processing facilities on both ends, a multi-use path for non-motorized users, and a focus on minimizing environmental impact during construction. Construction of the bridge began with an intensive ground improvement phase. On both the Canadian and American sides, the project required deep foundation stabilization due to soft soils and industrial legacy conditions. Thousands of concrete-filled steel piles were driven deep into the ground, many over 150 feet long, to support the massive load of the main pylons and approach structures. Vibrocompaction and dynamic replacement techniques were also applied in select areas to densify weak soils and ensure long-term settlement control. The signature feature of the bridge is its cable-stayed main span, which stretches more than 2,500 feet across the Detroit River. The two massive towers, each rising nearly 150 meters above the water, were constructed using climbing formwork systems with high-strength reinforced concrete placed in lifts and allowed to cure under strictly controlled environmental conditions. Each lift required careful coordination of embedded rebar cages, conduit for internal inspection systems, and multiple layers of quality control for alignment and geometric accuracy. The stay cables are arranged in a semi-fan pattern and connect to a composite steel concrete deck that is fabricated in modular segments. These segments are lifted into position by strand-jacking gantries placed atop the towers, and then post-tensioned into place as the structure progresses outward from both pylons in a balanced cantilever method. Because of the immense forces involved, cable anchorage zones in the deck were heavily reinforced and constructed using high-performance concrete to prevent cracking and fatigue over the bridge's lifespan. In parallel with the main span construction, the approach structures required extensive use of precast girders and segmental concrete box girders, supported on piers founded on deep drilled shafts and pile caps. Each approach segment had to be aligned precisely with the main span geometry to allow seamless connection once the cantilevers met at mid-span. Expansion joints, seismic isolation bearings, and cable dampers were installed to accommodate temperature changes, traffic vibrations, and potential wind-induced oscillations. Perhaps one of the most unique aspects of the Gordie Howe International Bridge is the inclusion of full customs and inspection plazas on both sides of the river, which had to be constructed concurrently with the bridge. These facilities involve complex building systems, large-scale pavement infrastructure, and real-time data integration with transportation networks. Stormwater management, energy efficiency, and border security technologies were embedded into their design from the outset.
Let's move over to the Russky Bridge in Russia next. Spanning the eastern Bosphorus Strait, this bridge connects the Russky Islands to the main city of Vladivostok. With a central span of 3,622 feet, the Russky Bridge holds the record of the longest cable-stayed bridge span in the world. Its construction was a formidable challenge, given the harsh weather conditions and deep waters of the strait. The bridge's pylons rise to an impressive height of 1,053 feet, making them among the tallest bridge towers globally. The construction process was a massive undertaking, involving 5,000 workers at its peak. These workers faced extreme weather conditions, including strong winds and freezing temperatures, which required the use of specialized construction techniques and materials. The bridge's deck, supported by 168 cables, was designed to withstand the dynamic forces of both traffic and natural elements, ensuring stability and safety. Each cable, made from high-strength steel, was meticulously anchored and tensioned to maintain structural integrity of the bridge. One of the key engineering feats was the construction of the bridge pylons. These towering structures were built using advanced slip-form techniques, allowing for continuous and rapid construction despite the challenging weather. The pylons were anchored deep into the seabed using massive concrete foundations, providing the necessary support for the bridge's immense span. Additionally, the use of high-performance concrete and corrosion-resistant materials ensured the bridge's durability in the harsh marine environments. The Russky Bridge also features state-of-the-art monitoring systems to continuously assess its structural health and detect any potential issues in real time. These systems are crucial for maintaining the bridge's integrity and ensuring the safety of thousands of vehicles and passengers that use it daily. Beyond its engineering achievements, the Russky Bridge has significantly boosted the local economy by improving access to Russky Island, which hosts major university and various research institutions.
But the underwater megaprojects can get much longer than that. The Baltic Pipe project was completed in 2022 at a cost of approximately 1.6 billion euros, and it stretches over 900 kilometers, forging a direct link between Norway's gas fields and Poland, with passages through Denmark. Its primary aim is to diversify energy sources and reduce Central and Eastern European countries' dependence on Russian gas, showcasing a pivotal shift towards sustainable and secure energy supplies. The construction of the Baltic Pipe involved laying underwater pipelines across the North Sea and the Baltic Sea, a challenging endeavor that required advanced engineering techniques. Specialized ships were deployed to lay the pipes on the seabed, ensuring minimal disruption to commercial navigation routes. This project is notable not just for its engineering achievements, but also for its role in enhancing political cooperation among European nations. By providing a stable, reliable source of natural gas, the Baltic Pipe supports Europe's goals of energy independence and sustainability, relying less on Russia's Nord Stream pipe. We travel to the country of Peru next, where the Olmos Transandino project is located. Carving a 20-kilometer tunnel directly through the heart of the Andes Mountains and completed in 2006, this project represents one of the most ambitious underground endeavors globally, not just for its length, but for its profound impact on the region's ecology and economy. Initiated to address severe water scarcity on Peru's arid Pacific coast, the tunnel channels water from the Huancabamba River on the Atlantic side of the Andes to the Pacific side. This engineering marvel plunges as deep as 2,000 meters below the mountain peaks, which is nearly 4 times deeper than the Channel Tunnel. The depth and complexity of tunneling through such diverse geological formations make the Olmos Tunnel a standout project far surpassing simpler ventures in both scale and technical challenges. Costing approximately $500 million, this project deployed one of the world's largest tunnel boring machines, nicknamed the Andean Giant. This machine faced unprecedented challenges due to the Andes' notorious seismic activity and the presence of tough silicified rock, which required custom-engineered cutter heads to break through. The tunnel now facilitates the transfer of 2 cubic meters of water per second, which is intended to irrigate 43,000 hectares of land, equivalent to the size of more than 60,000 football fields. Moreover, the Olmos project has introduced an innovative water management system that includes not only the tunnel, but also a vast network of canals and reservoirs designed to optimize water use across agricultural and energy sectors. The project's location in one of the most seismically active areas of the world required sophisticated geological surveys and adaptive construction techniques to mitigate potential earthquake damage. Despite this challenge, the completion of the Olmos Tunnel has transformed a once parched region into one of Peru's most fertile agricultural zones.
Unlike conventional bridge construction that relies on in-place assembly over active roadways, the 2nd Avenue Bridge replacement over I-94 in Detroit took a bold and modern approach, building the entire structure off-site and moving it into position in a single, coordinated operation. This method, known as self-propelled modular transport, allowed engineers to reduce highway closures dramatically while executing a highly complex structural replacement with precision and control. The original 2nd Avenue Bridge was a narrow, outdated crossing that no longer met the safety or capacity standards required for urban connectivity in the Midtown Detroit corridor. With the ongoing modernization of the I-94 freeway, it became essential to not only replace the bridge, but to do so in a way that minimized impacts to one of the busiest traffic arteries in the state. Traditional staged construction would have required extended lane closures, ongoing detours, and multiple phases spread out over months or even years. Instead, the project team designed a new, wider bridge structure that would be constructed entirely adjacent to the interstate in a staging area. This new structure, composed of steel plate girders and a concrete deck, was built on temporary supports known as falsework towers. The substructure, comprising abutments and approach walls, was prepared well in advance at the final bridge site using cast-in-place concrete supported on deep foundations, including driven H-piles embedded into firm strata beneath the interstate. Once the off-site construction was complete and all systems verified, the move operation was scheduled for a carefully planned weekend closure of I-94. The actual bridge move was performed using SPMTs, multi-axle, computer-controlled transport platforms capable of lifting and carrying massive loads with millimeter-level accuracy. The entire superstructure was lifted off its temporary falsework supports using hydraulic jacks integrated into the SPMTs. The system then slowly transported the bridge across the staging area, maneuvering over prepared access paths and aligning itself precisely with the final bridge bearings. During this process, crews on site continuously monitored bearing alignment, elevation, and lateral position, ensuring the bridge matched its abutment seat locations exactly. Once the bridge was in final position, it was slowly lowered onto elastomeric bearings, and mechanical connections were secured to tie the structure into the existing roadway network. The final stages of the operation included backfilling approach zones, paving transitions, and installing barriers and utilities, all tasks that had been prepared in advance to accelerate reopening. One major advantage of this move-in-place approach was that it compressed months of disruptive work into a matter of days. Rather than subjecting the corridor to prolonged construction noise, lane reductions, and detours, the SPMT method enabled a near instantaneous installation with minimal long-term disruption.
Let's talk about the Erasmus Bridge in Rotterdam, Netherlands, stretching 2,631 feet across the Neumaas River. This cable-stayed bridge is notable for its single asymmetrical pylon that rises 456 feet into the air. The bridge connects the northern and southern parts of Rotterdam, enhancing the city's infrastructure and promoting economic growth. The construction of the Erasmus Bridge prevented numerous engineering challenges, particularly due to its unique design and the heavy traffic it needed to support. The bridge's pylon, made of 8,000 tons of steel, was constructed on site using advanced techniques to ensure its stability and strength. The pylon's asymmetrical design required precise calculations and innovative construction methods to balance the forces exerted by the bridge's cables and deck. One of the key features of the Erasmus Bridge is its cable-stayed design, which includes 40 steel cables that fan out from the pylon to support the bridge deck. These cables were carefully tensioned to ensure even distribution of weight to minimize the movement under dynamic loads such as wind and traffic. The bridge deck itself is constructed from steel and concrete, providing the necessary strength to support both vehicular and pedestrian traffic. During construction, engineers faced the challenge of building the bridge over a busy waterway without disrupting river traffic. To address this, the main span of the bridge was built off-site and floated into position using barges. This method allowed for precise placement and minimized interruptions to the bustling port activities below. The Erasmus Bridge also incorporates a 300-foot bascule bridge section, which can be raised to allow larger ships to pass through. This section is one of the largest and heaviest bascule bridges in the world, with a counterweight system that ensures smooth and efficient operation. Since its completion, the Erasmus Bridge has become a vital artery for Rotterdam, significantly improving traffic flow and accessibility.
But how about a tunnel that has been connecting two countries for over 2 decades? Let's check out the Øresund Tunnel, which is part of the Øresund link that connects Denmark and Sweden, facilitating unprecedented connectivity between the two countries since its completion in 2000. This project, with a total cost of around 4 billion euros for the entire Øresund link, includes a bridge, an artificial island, and the tunnel itself, showcasing a blend of engineering ingenuity and cooperation across borders. Stretching 4 kilometers beneath the Øresund Strait, the tunnel complements the 8-kilometer bridge to form a comprehensive transport route. The construction of the tunnel employed the cut-and-cover method, where a trench was excavated on the seabed, and prefabricated tunnel sections were then lowered into place. The Øresund Tunnel has significantly reduced travel time between Denmark and Sweden, bolstering economic ties and cultural exchange. Next up is another underground Chinese megaproject called the Jinping Laboratory. This laboratory is the deepest underground lab in the world, located approximately 2,400 meters beneath the surface in the Jinping Mountain. This staggering depth surpasses that of other well-known underground facilities like the Sanford Underground Research Facility in the United States. Established in 2010, the Jinping Lab is designed for the detection of dark matter particles and other low-background experiments that require protection from cosmic radiation. The depth provides an overburden of 6,700 meters water equivalent, the highest of any laboratory in the world. Spanning an area of 20 square meters, the laboratory's construction involved excavating approximately 80,000 cubic meters of rock, a volume that underscores the massive scale of this project compared to smaller scientific setups, such as the Gran Sasso in Italy. One of the unique challenges faced during the construction of Jinping was managing the high water pressure prevalent at such depths, which necessitated the development of specialized waterproofing and pressure management systems. The Jinping Underground Laboratory is also a site of international collaboration, drawing scientists from across the globe to its deep earth cavern. Moreover, the laboratory's remote location and depth make it a logistical challenge, requiring the transportation of equipment and personnel through a single tunnel that connects the lab to the outside world.
It's time to move over to the Yavuz Sultan Selim Bridge in Turkey. Completed in 2016, it's a remarkable feat of modern engineering that spans the Bosphorus Straits, linking Europe and Asia. This bridge, with a main span of 4,619 feet, is one of the longest and widest suspension bridges in the world. Its construction required overcoming numerous engineering challenges, particularly the need to withstand significant seismic activity and harsh weather conditions typical of the region. The bridge tower soars to heights of over 1,056 feet, making them among the tallest bridge towers globally. These towers support a massive deck that carries 8 lanes of traffic and 2 railway lines, facilitating both vehicular and rail transportation across the Bosphorus. The construction process of the Yavuz Sultan Selim Bridge involved the use of advanced engineering techniques and materials. Over 700,000 cubic meters of concrete and 150,000 tons of steel were used in the bridge's construction, ensuring its robustness and durability. One of the critical components of the bridge is its cable system, comprising over 1.4 million meters of steel wire, which was meticulously spun on site to create the main cables. These cables are designed to support the immense weight of the bridge deck while allowing for flexibility and movement, essential for withstanding the dynamic forces exerted by traffic, wind, and potential earthquakes. The bridge also features state-of-the-art aerodynamic elements to minimize wind resistance and ensure stability under various weather conditions. The construction team implemented a range of innovative safety measures, including advanced monitoring systems to continuously assess the bridge's structural health and detect any potential issues in real time. These systems are crucial for maintaining the bridge's integrity and ensuring the safety of the thousands of vehicles and passengers using it daily. The bridge's strategic importance extends beyond transportation, as it's also supporting economic activities by facilitating the efficient movement of goods and people across a major international transit route.
The next project on our list is a tunnel that's connecting 2 major countries, the Fehmarn Belt Fixed Link. This ambitious project, with an estimated cost of 7.4 billion euros, is not just another infrastructure endeavor. It's a bold leap towards uniting regions and enhancing mobility in Europe by connecting Germany and Denmark. Spanning approximately 18 kilometers, it's poised to become the world's longest immersed tunnel, designed for both rail and road traffic. The construction employs the use of specially designed ships to lay sections of the tunnel on the seabed, a method that underscores the innovative spirit of this undertaking. The tunnel comprises 79 individual segments, each meticulously fabricated off-site, showcasing the meticulous planning and precision that underpin this colossal project. The planned completion date for this project is unknown, but they're aiming to open it somewhere in 2029. Moving over back to the United States, it's time to investigate the Soudan Underground Mine State Park. Nestled in the Vermilion Range of Minnesota, this project harbors the state's oldest and deepest iron ore mine, which commenced operations in 1882 and continued until 1962. This site has transitioned from a high-grade ore production facility to a hub for scientific research and public education. The mine's deepest sections extend nearly half a mile underground, setting it apart as one of the most substantial vertical shaft mines in the United States. During its 80 years of operation, the Soudan mine produced over 15.5 million tons of ore, a staggering amount that contributed significantly to the region's economic development. This production level was critical for the United States steel industry, particularly during both World Wars. Transforming the site into Soudan Underground Mine State Park involved significant effort and resources, with the state of Minnesota investing heavily to preserve this historical landmark. The transition included extensive renovations to stabilize old mine workings and adapt the underground tunnels for safe public tours and scientific research, specifically in physics. The park now hosts a state-of-the-art physics laboratory, which was established to study particle physics, including investigations into the elusive dark matter. This lab, located in the mine's lower levels, utilizes the Earth's natural shielding against cosmic rays to operate highly sensitive detectors, such as the MINOS experiment, which tracks neutrinos from the Fermilab in Illinois over a distance of 450 miles. A country that can obviously not be missing from this list is China, who has their own fair share of underwater megaprojects. Let's dive into the Kong-Zhuhai-Macau Bridge-Tunnel. Overcoming the physical and economic divide between Hong Kong and Zhuhai, this project was completed in October 2018, consisting of a series of bridges and tunnels spanning approximately 55 kilometers, making it one of the longest sea-crossing structures in the world. With a budget exceeding $18.8 billion, the project is designed to facilitate the flow of people and goods, strengthening connectivity and economic integration within the Pearl River Delta region. At the heart of this colossal structure is a 6.7-kilometer underwater tunnel, descending up to 40 meters below the sea level, seamlessly connecting two artificial islands. This tunnel was a critical solution to avoid disrupting the busy maritime lanes in the Pearl River estuary. The construction of the tunnels required innovative engineering techniques, including the use of immersed tube tunnel methods for the underwater sections.
Next, we turn our attention to the Humber Bridge in the United Kingdom, an iconic landmark in the realm of bridge construction. Completed in 1981, the Humber Bridge held the record as the world's longest single-span suspension bridge until 1998, with a main span measuring an impressive 4,626 feet. This feat of engineering connects the East Riding of Yorkshire with North Lincolnshire, significantly improving travel times and boosting economic ties between the two regions. Constructed at a cost of approximately £98 million, which would equate to around $500 million today, the Humber Bridge was a monumental project of its time. The design and construction of the Humber Bridge posed numerous challenges, not least of which was its location over the Humber estuary, known for its deep waters and strong tidal currents. The bridge's two massive towers, each rising 510 feet above the water, were constructed using a combination of reinforced concrete and steel, providing the necessary strength and stability to support the immense weight of the bridge deck. The main cables, each composed of 14,948 strands of high-tensile steel wire, were spun in situ using a complex and labor-intensive process that ensured they could withstand the forces exerted by the span and the variable weather conditions. One of the key construction techniques involved the use of floating caissons for the foundations, which were sunk into the estuary bed to provide a stable base for the towers. This method required precise engineering and careful coordination to ensure the caissons were placed accurately and securely. Additionally, the bridge was designed to allow for thermal expansion and contraction, as well as the dynamic loads imposed by traffic and wind, incorporating expansion joints and flexible cables that could accommodate these movements.
It's time to travel back to Norway for another incredible underwater project. The Oslofjord Tunnel serves as a vital link beneath the waters of the Oslofjord, connecting the regions of Østfold and Buskerud. Completed in 2000 at a cost of around $84 million, this underwater tunnel significantly reduces travel time between Oslo and the cities on the fjord's eastern side, fostering economic and social integration in the area. Spanning 7,306 meters, it is one of the longest underwater road tunnels in Norway, with a descent reaching 134 meters below sea level at its deepest point. The construction of the Oslofjord Tunnel was a complex engineering challenge, requiring the use of a drill and blast technique to carve through the rock beneath the fjord. Safety features within the tunnel, such as comprehensive ventilation systems and emergency exits, are paramount, reflecting Norway's commitment to road safety. Its construction underscores the balance between technological advancement and environmental stewardship, embodying Norway's approach to sustainable development. Now let's move to an underwater project that does not yet exist, and that would break many records if it was being constructed. The Transatlantic Tunnel, connecting New York to London, is a testament to human ambition and engineering prowess. Staying in the United States, let's visit the Delaware Aqueduct, renowned as the world's longest continuous underground tunnel. Spanning an extraordinary 85 miles from the Rondout Reservoir in the Catskills to the Hillview Reservoir in Yonkers, New York, this aqueduct is crucial, supplying about 50% of New York City's fresh water. It was constructed between 1939 and 1945, burrowing as deep as 1,500 feet beneath the Hudson River. Designed to transport roughly 600 million gallons of water daily, the aqueduct features a 13.5-foot diameter, lined entirely with concrete to ensure efficient water flow and structural integrity. The construction required the mobilization of 17,000 workers who faced the formidable challenge of excavating through solid rock and managing high-pressure water ingress. Innovative for its era, the project utilized both tunnel boring machines and traditional drilling and blasting methods. Operating under pressures that can exceed 200 psi, the structural design of the aqueduct was a complex undertaking. Engineers had to develop special concrete formulations and construction techniques to cope with the pressures equivalent to being 460 feet underwater. Initially costing about $160 million in 1940, which is about $2 billion today when adjusted, the Delaware Aqueduct's financial implications were significant. Beyond the immense cost, the project stirred environmental and social controversies, including the displacement of communities and substantial ecological impacts due to its construction. In terms of maintenance, the aqueduct has not been without its problems either. It suffers from leaks that lose up to 35 million gallons of water per day, necessitating a major repair initiative. A $1 billion project is currently underway, which includes the construction of a 2.5-mile bypass tunnel around the most severely affected section.
It's time to talk about the Rio-Antirrio Bridge in Greece, officially known as the Charalaos-Trikopis Bridge. Completed in 2004, this cable-stayed bridge spans nearly 1.8 miles across the Gulf of Corinth, making it one of the longest multi-span cable-stayed bridges in the world. The bridge significantly improves connectivity and travel efficiency in the region, which previously relied on ferry services. Constructing the Rio-Antirrio Bridge presented numerous engineering challenges, primarily due to the deep waters, strong seismic activity, and high winds in the Gulf of Corinth. The bridge's foundations were a critical aspect of the project, designed to withstand these harsh conditions. Each of the 4 main pylons is anchored to the seabed using a combination of gravity caissons and driven piles. These caissons were filled with concrete and gravel, providing a stable and resilient foundation capable of withstanding seismic forces and soil liquefaction. The bridge's pylons, rising 492 feet above the water, were constructed using high-strength concrete and designed to be flexible enough to absorb seismic shocks. This flexibility is essential in an earthquake-prone area, allowing the bridge to move slightly with the seismic waves, rather than resisting them rigidly, which would risk structural damage. Additionally, the pylons are equipped with hydraulic dampers to further mitigate seismic impacts. The main span of the bridge is supported by 368 cables, arranged in a fan-like pattern that distributes the weight to the bridge deck evenly. These cables are made of high-tensile steel and were carefully tensioned to ensure optimal load distribution. The bridge deck itself is constructed from pre-stressed concrete segments, which were cast on shore and then transported to the site for installation. This method allowed for high precision and quality control during construction. The Rio-Antirrio Bridge also incorporates an innovative expansion joint system that accommodates thermal expansion and contraction, ensuring the bridge remains stable and functional across a range of temperatures. This system is crucial for maintaining the bridge's integrity over its lifespan, particularly in a region with significant temperature variations.
Few infrastructure projects in the northeastern United States have so comprehensively redefined regional mobility as the construction of the Governor Mario M. Cuomo Bridge. Spanning the Hudson River between Tarrytown and Nyack, this modern twin-span structure replaced the aging Tappan Zee Bridge, which had served for over 6 decades but was increasingly unable to meet the demands of 21st century traffic, safety, and structural performance requirements. The replacement effort was not only monumental in scale, but also served as a showcase of accelerated design build execution, seismic resilience, and long-span cable-stayed bridge engineering. Construction began with an extensive program of pile driving and cofferdam installation in the river's soft glacial sediments. More than 1,000 piles were driven to create the foundations for the main span towers and approach piers, with many of them extending over 200 feet below the river surface to reach competent strata. These piles were either steel pipe piles or concrete-filled steel cylinders driven using high-capacity hydraulic hammers aboard floating barges. Each pile had to be carefully aligned to meet strict tolerances, and dynamic load testing was performed regularly to verify bearing capacity. Central to the structure are the cable-stayed main spans, each carrying 4 lanes of traffic with additional space for emergency shoulders and a shared-use path. The twin main span towers, constructed with reinforced concrete, rise from pile-supported cofferdams and were built incrementally using jump-form systems. These towers house the anchorages for the stay cables, which are arranged in a semi-fan configuration and composed of galvanized steel strands enclosed in protective sheathing. Each cable was tensioned individually using strand jacks, and their load paths were continuously monitored throughout installation to maintain even deck camber and prevent distortion. The bridge's deck was constructed using precast concrete panels and structural steel girders. These panels were fabricated off-site and barged to the work zone, where they were lifted into place by gantry cranes and secured with high-strength post-tensioning systems. By utilizing modular construction, the project team reduced field labor intensity and maintained strict quality control over concrete finishes and rebar placement. Simultaneously, orthotropic deck sections were integrated into specific areas where weight savings were essential, particularly near the tower anchorages. Wind loads and thermal expansion across the bridge's more than 3-mile length were key design considerations. Expansion joints with built-in damping systems were installed at each abutment and tower transition. The bridge is also equipped with smart monitoring systems embedded within its structure, capable of measuring strain, tilt, temperature, and traffic load in real time. On the western span, a dedicated bicycle and pedestrian path was constructed, complete with belvederes for scenic viewing and interpretive signage. This element, though minor in structural weight, required careful coordination with the main deck construction to maintain alignment, loading distribution, and railing continuity. The lighting system was also integrated directly into the bridge structure, minimizing the need for maintenance access while providing full-spectrum LED visibility and programmable displays for special events.
It's time to talk about one of the most recognized landmarks in the world, the Sydney Harbour Bridge in Australia, completed in 1932. Spanning 1,650 feet across Sydney Harbour, this bridge connects the bustling central business district with the vibrant North Shore. Its design, characterized by a massive steel arch rising 440 feet above the harbour, earned it the nickname the Coat Hanger. The bridge's construction utilized 52,800 tons of steel, assembled using a technique that involved building the 2 halves of the arch simultaneously and then joining them in the center, a method requiring precise engineering and coordination. The construction was a colossal endeavor, involving over 1,400 workers at its peak. These workers faced perilous conditions, often working at dizzying heights without the safety standards that are common today. Despite these challenges, the project was completed on schedule, thanks to the rigorous planning and the application of cutting-edge engineering techniques of the era. The bridge's deck, supported by massive steel trusses, was designed to accommodate both vehicular and rail traffic, reflecting its essential role in Sydney's transportation network. One of the remarkable engineering achievements was the method used to erect the steel arch. Each half of the arch was built from pylons and gradually extended toward the center. When the 2 halves were complete, they were carefully aligned and connected, a process that required meticulous precision. And this method not only showcased the engineering capabilities of the time, but also highlighted the daring nature of the construction process. In addition to the arch, the Sydney Harbour Bridge features 4 large granite-faced pylons, which, although not structurally necessary, add to the bridge's aesthetic appeal. These pylons also house various facilities, including lookout points that offer panoramic views of the Sydney Harbour and the city skyline.
As the rising arc of twin basket handle arch bridges took shape over the Mississippi River, the transformation of the I-74 corridor between Bettendorf, Iowa, and Moline, Illinois, entered one of its most critical and technically ambitious phases. The construction of the new I-74 Mississippi River Bridge was not merely a replacement of aging infrastructure, it was a complete reimagining of regional connectivity, driven by modern standards for traffic volume, safety, and structural resilience. The original bridge system, composed of 2 separate spans constructed decades apart, had long been overcapacity and structurally obsolete, necessitating a solution that would carry 4 lanes of traffic in each direction, with substantial shoulders and multimodal accommodations. Foundation work for the main river crossing demanded meticulous geotechnical investigations due to the presence of complex riverbed conditions. Deep caissons and drilled shafts were deployed to reach competent rock, with many of the drilled shafts extending over 100 feet into the bedrock below the Mississippi's muddy floor. This phase involved the use of massive steel casing, oscillators, and reverse circulation drilling techniques to ensure shaft integrity in an environment challenged by underwater currents and variable sediment layers. Cofferdams were constructed to create dry working conditions for pier construction, each one engineered to resist the high hydrostatic pressures of the river during seasonal flooding. The signature basket handle arch design was selected for both aesthetic and structural performance. These arches rise more than 100 feet above the deck and were fabricated in large segments off-site, then transported by barge to the erection location. The erection sequence was tightly choreographed. Arch ribs were lifted and pinned using floating cranes during periods of calm river flow, with crews performing high elevation bolting and welding operations within tight tolerances. Each arch rib section was temporarily braced and connected via knuckle joints and box diaphragms until the entire arch structure was self-supporting. The steel itself was weathering grade, chosen to reduce long-term maintenance needs and withstand the extreme freeze-thaw cycles common to the upper Midwest. Suspended below each arch is a post-tensioned concrete deck carried by steel hangers arrayed in a vertical configuration. The bridge deck was cast in place using a traveling formwork system that advanced span by span. Epoxy-coated rebar, high-performance concrete mixers, and continuous monitoring of curing conditions ensured long-term durability. Expansion joints were minimized through the use of integral abutments and deck continuity, reducing maintenance complexity. Parallel to the main river spans, approach structures on either side required extensive reconstruction and realignment of existing highway infrastructure. Mechanically stabilized earth walls and drilled shaft-supported piers form the backbone of the approaches. The coordination of traffic staging during construction was a major challenge, as portions of the existing bridge needed to remain in service throughout the process. Temporary crossovers, stage demolitions, and nighttime steel girder installations were part of a detailed traffic management strategy.
Let's move over to the next mega project. The Penang Second Bridge, officially named the Sultan Abdul Halim Muazzam Shah Bridge, is a remarkable feat of modern engineering in Malaysia. Opened to the public in 2014, this bridge stretches 15 miles across the Penang Strait, connecting Batu Kawan on the mainland to Batu Maung on Penang Island. As the longest bridge in Southeast Asia, it has significantly improved connectivity and economic activity in the region. The construction of the Penang Second Bridge was an ambitious project that took nearly 6 years to complete and cost $1.1 billion. The project involved thousands of workers and utilized advanced engineering techniques to overcome the challenges posed by the strait's deep waters and strong currents. The bridge's design features dual carriageways and 2 lanes in each direction, supported by a series of precast concrete segments. These segments were produced onshore and transported to the construction site, where they were carefully positioned using specialized equipment. This method ensured high precision and quality control, vital for the bridge's durability and safety. One of the most significant engineering challenges was constructing the main navigational span, which is 820 feet long and 100 feet high, allowing large vessels to pass beneath without obstruction. This span is supported by cable-stayed structures anchored to pylons rising from the seabed. The cables, made from high-strength steel, were meticulously tensioned to provide optimal support for the bridge deck, balancing the loads from traffic and environmental forces. To ensure the bridge's longevity, the construction incorporated several advanced features, including a robust foundation system. The piers were driven deep into the seabed to withstand seismic activity and the constant movement of the waters. Additionally, the bridge is equipped with a comprehensive monitoring system to track structural health and detect any potential issues in real time.
Beneath the southern skyline of Portland, Oregon, the Sellwood Bridge replacement project unfolded as a carefully orchestrated effort to modernize a century-old crossing while respecting the constraints of an urban setting and a sensitive river environment. Originally opened in 1925, the existing structure had long been structurally deficient and functionally obsolete. It carried tens of thousands of vehicles per day on a narrow, deteriorating deck with no shoulders and minimal pedestrian accommodations. The new bridge would not only replace the failing structure, but also vastly improve safety, seismic resilience, and multimodal capacity. The design of the replacement bridge called for a deck arch structure which would span the Willamette River with minimal disruption to the waterway and surrounding neighborhoods. Prior to any new construction, engineers faced the unique challenge of what to do with the existing bridge. Instead of fully demolishing it up front, a temporary solution was implemented. The original steel truss was shifted laterally, intact, onto temporary piers constructed just downstream. This extraordinary lateral slide operation allowed the old bridge to remain in service while the new bridge was built in its original alignment. The lateral move required precise hydraulic jacking systems and heavy-duty rollers. Crews disconnected the truss from its existing piers and then slowly slid the entire structure onto a set of temporary supports built on drilled shafts. This move, executed in just a few hours after weeks of preparation, cleared the path for demolition of the original concrete piers, many of which had suffered extensive corrosion and were no longer structurally viable. With the original alignment clear, construction of the new bridge began with installation of deep foundation elements, including drilled shafts socketed into bedrock beneath the riverbed. These shafts would support the new reinforced concrete piers, which in turn carried the load of the deck arch. The arch segments were constructed using a balanced cantilever method, with concrete segments cast in place and post-tension to maintain structural integrity as they extended symmetrically from each side of the river. The bridge deck itself was cast in segments atop the arch ribs using a system of falsework and custom-formed travelers. The deck accommodated 2 standard travel lanes in each direction, generous bike lanes, and wide sidewalks on both sides, features entirely absent from the original structure. In addition, the deck design included integrated stormwater treatment systems to capture and filter runoff before it entered the Willamette River. As the new bridge took shape, utilities were relocated, traffic patterns shifted, and seismic isolators were installed beneath critical components to provide flexibility in the event of an earthquake. Steel reinforcement was designed with corrosion resistance in mind, and all concrete elements were specified with admixtures tailored to the region's wet climate. Once the new structure was complete and fully operational, the old temporary bridge was dismantled and removed from its temporary supports. Final phases included landscaping, approach road improvements, and installation of aesthetic lighting and railing features to blend the bridge with its urban and natural context.
Let's transition to another underwater project that is connecting cities called the Busan-Geoje Fixed Link. Spanning an impressive length of 8.2 kilometers, this fixed link connects the bustling city of Busan with the scenic island of Jeoje in South Korea, serving as a vital artery that significantly reduces travel time. Constructed at a cost of approximately $800 million, the project was completed in 2010 after 5 years of relentless work. The fixed link is a hybrid structure, comprising both bridges and underwater tunnels, ingeniously designed to navigate the challenges posed by the area's deep waters and heavy marine traffic. The centerpiece of this engineering feat is a 3.7-kilometer immersed tunnel, one of the longest of its kind in the world, which plunges beneath the sea to allow ships to pass unimpeded above. Despite its successes, the project was not without its challenges. Environmental concerns were raised regarding the impact on the marine ecosystem, leading to stringent measures being implemented to mitigate damage. Financial obstacles also loomed large, with debates on the project's cost-effectiveness and the burden on public resources sparking rigorous discussions. It's time to travel to Poland for the next project. The Wieliczka salt mine in Poland is an astonishing subterranean network that stretches to depths of up to 327 meters or 1,073 feet below the surface, covering an expansive area of 2.4 million square meters. Operational for over 700 years since its inception in the 13th century, the mine is one of the world's oldest continuously running salt mines, only ceasing commercial salt production in 2017 due to flooding and the low price of salt on the global market. This historic mine features a labyrinth of tunnels, chambers, and galleries that extend over 178 miles, though only a small portion is accessible to the public. By comparison, the equally historic but much shallower Kura salt mine in Pakistan extends just 25 miles of passages. One of the mine's most unique attributes is its underground city, which includes chapels, a cathedral, and numerous sculptures all carved from rock salt by the miners. Financially, the development of Wieliczka salt mine over the centuries has involved significant investment, particularly in its conversion into a major tourism and health resort. The site now attracts approximately 1.2 million visitors annually, generating substantial revenue that supports its preservation and the local economy. Throughout its long history, Wieliczka has faced numerous challenges, including the threat of mine flooding, which on several occasions risked catastrophic collapses. These were mitigated through modern engineering efforts that included the installation of high-volume pumps and new drainage systems, ensuring the mine's stability and the safety of its visitors. Besides that, the preservation of this UNESCO World Heritage Site involves complex conservation practices. The saline environment, which is beneficial for health, poses a constant threat to the mine's structural integrity, accelerating the deterioration of wooden structures and necessitating continuous maintenance efforts.
Let's move over to the United States for the New River Gorge Bridge. Spanning 3,030 feet across the New River Gorge, this arch bridge boasts a main span of 1,700 feet, making it one of the longest single-span arch bridges in the world. The bridge sits 876 feet above the New River, offering breathtaking views and dramatically improving transportation in the region. The construction of the New River Gorge Bridge was a monumental task, requiring innovative solutions to the challenges posed by the gorge's rugged terrain and the river below. The design utilizes a steel arch chosen for its strength and ability to span long distances without the need for support piers in the river, which would have been difficult to construct and maintain. One of the most impressive aspects of the construction process was the method used to assemble the arch. Prefabricated sections were lifted into place using cables strung across the gorge. This method required precise engineering and coordination to ensure each section was correctly aligned and secured. The steel used in the bridge's construction was specially treated to withstand the area's environmental conditions, ensuring its durability and longevity. The bridge's deck, supported by the arch below, carries 4 lanes of traffic and has significantly reduced travel times between the region's communities. Before the bridge's construction, travelers had to navigate a treacherous 40-minute journey down narrow, winding roads to cross the gorge. The New River Gorge Bridge has cut the travel time to less than a minute, fostering development and improving access to the area's natural beauty.
It's time to visit Norway, which has constructed a crucial underwater project called the Ormen Lange gas pipeline. Spanning an impressive 1,200 kilometers, it connects the Ormen Lange field in the Norwegian Sea to the United Kingdom, specifically to the processing plant at Nyhamna, Norway. Commissioned in 2017, this pipeline plays a crucial role in securing energy supplies in the region, marking a significant achievement in the field of energy infrastructure. Constructed at a cost of over $10 billion, the Ormen Lange gas pipeline's engineering required innovative solutions to navigate the challenging deep water conditions of the Norwegian Sea, including depths of up to 100 meters. This project also stood out for its environmental and technical challenges, particularly the need to minimize impacts on the delicate marine ecosystem and address the harsh conditions found in the North Sea. Located in Lead, South Dakota, the Sanford Underground Research Facility is a pinnacle of science, situated a breathtaking 4,850 feet below the surface. This facility, which has repurposed the former Homestake gold mine, now serves as a forefront for scientific exploration shielded from cosmic interference. The transformation from a bustling gold mine to a sophisticated scientific research hub required an investment of over $600 million. At its operational peak, the Homestake mine produced approximately 40 million ounces of gold. The mine's extensive network of tunnels, which total over 370 miles, provides the necessary infrastructure for the project's deep underground science laboratories. The project initially faced significant opposition due to concerns over environmental impact and the stability of old mine workings. There were fears about water contamination and surface subsidence, which led to stringent regulatory reviews and the implementation of sophisticated water treatment facilities. The facility now houses multiple laboratories where over 500 scientists from around the world conduct experiments. The depth of the facility provides over 4,850 feet of rock cover, which effectively shields the laboratory from about 99.5% of cosmic radiation that would otherwise interfere with sensitive experiments. It's time to move on to one of the biggest pipeline megaprojects in the world, called the Nord Stream gas pipeline. Stretching beneath the Baltic Sea to connect Russia with Germany, this strategic pipeline, operational since November 2011, spans approximately 124 kilometers, making it one of the longest offshore gas pipelines in the world. With a total project cost estimated at 8.8 billion euros, the Nord Stream has the capacity to transport up to 55 billion cubic meters of natural gas annually, playing a crucial role in ensuring energy security and diversification of supply routes in Europe. Constructed using state-of-the-art technology, the pipeline comprises two parallel lines, each made from tens of thousands of steel pipes welded together on board specialized vessels. These pipes, coated for corrosion resistance, were laid on the seabed by some of the world's most advanced laying ships, navigating through challenging marine conditions. Despite its technical achievements, Nord Stream has been mired in controversy. Critics argue that it increases European dependency on Russian gas, posing geopolitical risks. Environmental groups have also raised concerns about the potential impacts on the Baltic Sea's delicate ecosystem. Yet, proponents highlight its contribution to energy security and lower carbon emissions compared to coal and oil.
We have to talk about the 1915 Canakkale Bridge next, which is located in Turkey. Spanning the Dardanelles Strait, this suspension bridge connects the towns of Galibalu on the European side with Lapseki on the Asian side. With a main span of 6,637 feet, it is the longest suspension bridge in the world, surpassing Japan's Akashi Keikyo Bridge. The construction of the 1915 Canakkale Bridge was a monumental task that involved overcoming numerous engineering challenges. The project, which cost approximately 2.8 billion euros, employed thousands of workers and utilized state-of-the-art technology and materials. The bridge's design includes two massive towers, each standing 1,043 feet tall, constructed using high-strength steel. These towers support the main cables, which are composed of over 162,000 miles of steel wire, meticulously spun on site to ensure optimal tension and load distribution. One of the key challenges was constructing the bridge in a seismically active area. To address this, engineers incorporated advanced seismic protection measures, including special bearings and dampers that allow the bridge to absorb and dissipate seismic energy. These features are crucial for ensuring the bridge's stability and safety in the event of an earthquake. Additionally, the bridge is designed to withstand the strong winds and harsh environmental conditions typical of the Dardanelles Strait. The bridge deck, which carries 6 lanes of traffic, was constructed using prefabricated sections. These sections, each weighing several hundred tons, were transported to the site by barges and lifted into place using specialized cranes. This method allowed for precise alignment and efficient assembly of the bridge deck, minimizing construction time and ensuring high-quality craftsmanship.
Now it's time for a different type of underwater project, and for that we have to travel to the United States, where the Lake Mead Intake No. 3 tackles the critical issue of water scarcity. This monumental project, costing an impressive $817 million, was driven by the urgent need to secure a reliable water supply for Las Vegas, a city that depends heavily on the waters of Lake Mead. Initiated in 2008 and completed in 2015, the project involved drilling a 3-mile-long tunnel beneath Lake Mead, one of the largest man-made lakes in the United States. This was no ordinary task. It required the use of a 1,500-ton tunnel boring machine, cutting through the earth at depths reaching 600 feet below the lake's surface. The purpose? To construct a new intake capable of drawing water from the lake's depths, ensuring access to clean water even as lake levels fluctuated perilously low due to prolonged drought conditions. The construction of intake number 3 was not just about securing a water source, it was about innovating for the future. Engineers and workers faced the daunting challenge of working in an environment where temperatures soared, and the risk of flooding within the tunnel was a constant threat. Staying in Asia, we have to talk about Beijing's massive underground subway megaproject next. With its first line opening in 1969, the network has expanded to include 25 lines, encompassing over 700 kilometers of track and approximately 428 stations, making it one of the longest metro systems globally. This sheer size surpasses many other major systems, such as New York's subway, which measures about 380 kilometers in length. Diving into the depths, the Beijing subway's deepest point is at the Daxing Airport Express line, which reaches 30 meters below the ground. The construction costs for this colossal network have amounted to billions of dollars, with recent expansions like the Line 7 and Line 14 collectively costing over $7.3 billion. One unique aspect of the Beijing subway is its adaptation to the city's geological conditions, which include areas of high seismic activity. The system is designed with earthquake resistance features that allow it to withstand tremors, a critical capability not integrated into many older and less robust subway designs around the world. Moreover, the Beijing system incorporates state-of-the-art technologies such as contactless ticketing, high-speed train sets capable of exceeding speeds of 100 kilometers per hour, and an automated ventilation system that is considered one of the most advanced in the world. Challenges have been persistent throughout its development, including issues with overcrowding, particularly during peak hours where some lines see passenger loads far exceeding their designed capacity. To combat this, the government has implemented dynamic pricing models during rush hours and has continuously expanded lines and added new ones to distribute passenger flow more evenly. As the system continues to grow, with plans to exceed 1,000 kilometers by 2030, it remains a critical component of Beijing's urban landscape.
It's time to move to the Storebaelt Bridge in Denmark, also known as the Great Belt Bridge. The bridge complex connects the islands of Zealand and Funen, significantly enhancing transportation and commerce in the region. The total length of the bridge system is approximately 11 miles, with the most impressive feature being the East Bridge, a suspension bridge with a main span of 5,328 feet, making it one of the longest suspension bridge spans in the world. Constructing the Storebaelt Bridge was a complex task that involved overcoming numerous engineering and environmental challenges. The project required the efforts of 8,000 workers and cost approximately $3 billion. The East Bridge's two massive pylons, standing at 833 feet tall, were constructed using high-strength concrete and were anchored deep into the seabed to provide stability against the strong winds and currents of the Great Belt Strait. One of the key engineering feats was the installation of the bridge's main cables, which are made up of 18,648 individual wires bundled together. These cables were meticulously spun on site and tensioned to support the enormous weight to the bridge deck, which carries both road and rail traffic. The deck itself is a marvel of modern engineering, designed to withstand the dynamic forces of wind, temperature changes, and the current weight of heavy traffic. The West Bridge, a box girder bridge, spans nearly 4 miles and carries both road and rail traffic. It required the construction of large concrete piers, which were precast on shore and then transported to their final positions using specially designed barges. This method ensured precision placement and minimized disruptions to the maritime traffic below. The Storebaelt Bridge also includes a 5-mile-long tunnel, the world's second longest combined rail and road tunnel. This section was constructed using a combination of immersed tubes and bored tunnel techniques, ensuring a safe and efficient route for vehicles and trains.
Crossing the North Sea, it's time to visit Norway for a massive underwater megaproject. Norway's Coastal Highway project is an unparalleled infrastructure endeavor aimed at revolutionizing travel along the country's rugged western coast. With an estimated cost of $40 billion, this ambitious project seeks to eliminate the need for 7 ferry crossings by connecting the cities of Kristiansand in the south to Trondheim in the north through a continuous, ferry-free highway. Spanning over 100 kilometers, it involves the construction of bridges, tunnels, and causeways designed to navigate the challenging Norwegian underwater terrain and weather conditions. A highlight of the project is the proposed construction of the world's longest and deepest submerged floating tunnel, a feat of engineering that exemplifies Norway's innovative approach to overcoming geographical obstacles. This tunnel alone, part of the route across the Sognefjord, is expected to stretch 3.7 kilometers in length and reach depths of up to 392 meters below sea level. Scheduled for completion in 2050, the Coastal Highway project not only aims to significantly reduce travel time across the western coast, but also to boost economic growth and connectivity in remote regions. But what about an impressive underground traffic tunnel located in the United States? The Port of Miami Tunnel project is designed to streamline traffic flow to Miami's bustling port facilities while significantly reducing urban congestion on downtown streets. Completed in 2014, this $1 billion project introduced a 4,200-foot-long twin-tube tunnel connecting the MacArthur Causeway on Watson Island with the Port of Miami on Dodge Island. With sections reaching depths of up to 120 feet below the Miami harbor, the Port of Miami Tunnel delves deeper than many other urban infrastructure projects, such as the Big Dig in Boston, which averages 65 feet deep. This depth was critical to allow unrestricted movement of cruise ships and cargo freighters, which frequent one of the busiest cruise ports in the world. The tunnel's construction utilized a world-class tunnel boring machine named Harriet, which was specifically designed for the Miami geology. This 42.3-foot diameter machine was one of the largest of its kind deployed in the United States. Financially, the tunnel project was structured through a public-private partnership, the first of its kind in Florida's history. The tunnel is equipped with state-of-the-art safety systems, including 91 CCTV cameras, 400 radio antennas, 44 jet fans, and 28 fire hydrants, set within fire-resistant concrete walls. These comprehensive measures surpass the setups found in smaller tunnels where budget constraints often limit such extensive safety implementations. Despite its successful completion, the Port of Miami Tunnel project encountered numerous challenges. Initial geological surveys underestimated the complexity of the Miami limestone, leading to adjustments in the tunneling work that delayed the project by several months. Moreover, the project's deep excavation close to densely populated urban areas and vulnerable marine environments posed significant logistical and environmental hurdles, necessitating rigorous compliance with stringent regulations.
We move over to Canada next, where the Confederation Bridge is located. Connecting Prince Edward Island to New Brunswick, the bridge is a marvel of modern engineering, completed in 1997. This 8-mile-long structure is the world's longest bridge over ice-covered waters, revolutionizing access to and from the island. The construction of this impressive bridge was an ambitious project that involved overcoming numerous engineering challenges posed by the harsh marine environment of the Northumberland Strait. The construction process employed over 5,000 workers and cost around $1 billion Canadian dollars. The design consists of a series of 44 high-performance concrete piers, each spaced approximately 820 feet apart. These piers were constructed on shore in a specially designed dry dock and then floated out to their positions using a fleet of barges. This method allowed for precise placement and alignment, ensuring the stability of the bridge. One of the most notable challenges was constructing the piers to withstand the extreme forces exerted by ice flows, which can reach thicknesses of up to 3 feet in winter. To address this, the piers feature an ice shield that deflects ice downward, breaking it into smaller, less forceful pieces. This innovative design ensures the bridge remains intact even during the harshest winter conditions. The superstructure of the Confederation Bridge, made from post-tensioned concrete, was designed for durability and minimal maintenance. Post-tensioning involves inserting high-strength steel cables through ducts in the concrete and then tensioning them to compress the concrete, significantly enhancing its strength and durability. This technique was crucial for ensuring the bridge could withstand the region's severe weather and temperature fluctuations. The bridge deck, rising to a height of 197 feet at its highest point, allows for passage of marine traffic. It carries 2 lanes of traffic and includes safety features such as a continuous concrete barrier and windshields to protect vehicles from the strong winds common in that area. The bridge is equipped with a sophisticated monitoring system that provides real-time data on structural health, ensuring its safety and longevity.
In an environment where minimizing disruption to major interstate corridors is paramount, the I-95 bridge replacement in Westport, Connecticut, demonstrated the full potential of accelerated bridge construction methods, specifically the lateral slide technique. This project involved replacing a structurally deficient bridge over Saugatuck Avenue. one of the busiest stretches of I-95 in the region, and doing so within a matter of days rather than months. The strategy required meticulous preparation, extensive off-site construction, and flawless execution during a very short highway closure window. The existing structure, carrying both northbound and southbound traffic, had reached the end of its service life. Deterioration in the substructure and deck made full replacement necessary, but the surrounding context, a dense suburban area with no practical detour options, meant that a traditional replacement approach was unfeasible. Engineers turned to a plan that would pre-build the new bridge spans adjacent to the existing alignment, then slide them into position during a single, carefully scheduled weekend closure of I-95. Before anything could be moved, a complex network of temporary supports, approach transitions, and hydraulic jacking systems had to be prepared. Construction crews built the new bridge structures on temporary foundations parallel to the active highway lanes. These new spans consisted of precast concrete deck panels integrated with steel girders, forming a composite superstructure. All connections, reinforcements, drainage components, and lighting conduits were pre-installed to reduce on-site finishing work after the move. While traffic continued to flow on the existing bridge, crews below worked on the new bridge's final foundation and abutment construction. These included concrete abutments supported by deep foundation systems, such as driven piles, along with bearing pads designed specifically to accept the sliding load. The horizontal slide surface was engineered using Teflon-coated pads and stainless steel slide tracks designed to minimize friction during the move. When the designated closure window arrived, the entire section of I-95 was shut down, and demolition crews moved quickly to remove the existing bridge. This required heavy excavators, saw-cutting equipment, and debris haulers working in synchronized shifts to clear the area within hours. As soon as the old structure was out of the way, hydraulic jacks were engaged to push the new bridge spans laterally onto the permanent abutments. This slide was conducted at a controlled pace, typically a few feet per hour, with continuous monitoring to ensure alignment, levelness, and bearing engagement. Once the new bridge was in place, the final phase included forming and pouring the deck closure joints, completing the approach slabs, connecting utility runs, applying waterproofing membranes, and finishing the surface paving. Precast parapets and guardrails were already attached to the new deck, eliminating the need for extensive post-move safety installations. Within just a few days, traffic was flowing again over a brand new structure with enhanced load capacity, seismic performance, and modern safety features. The I-95 bridge slide in Westport became a prime example of how advanced construction methods can be leveraged to perform full-scale bridge replacements in compressed timelines without sacrificing quality, safety, or functionality.
While underwater tunnels are usually used for mobility, Canada is utilizing them for something else with their Seymour-Capilano water filtration project. Nestled in the verdant landscapes of British Columbia, Canada, the tunnel is an engineering marvel designed to ensure the provision of clean, safe drinking water to the Vancouver metropolitan area. This project is distinguished by its expansive network of tunnels, stretching over 7.1 kilometers, which serve as conduits for transferring water between the Seymour Reservoir and the Capilano Reservoir. Constructed at a cost of over 600 million Canadian dollars, the project underscores the critical importance of sustainable water management in urban planning. The construction process showcased a blend of traditional tunneling methods and modern technological innovations. 2 massive tunnel boring machines were deployed, each weighing over 1,000 tons, carving through the mountainous terrain with precision. The project became operational in May 2010, and ever since it has been a vital part of the region. But what about a gigantic underground sewage system? Singapore's deep tunnel sewage system is an ambitious underground wastewater management project designed to meet the country's water needs through the 21st century. Completed in 2008, Phase 1 of the project is a key component of Singapore's approach to sustainable water use, demonstrating foresight in urban planning and engineering. Spanning a length of 48 kilometers, the main tunnel of the system is situated up to 50 meters below the surface. This depth is considerably greater than many urban sewer systems, such as those in older parts of Paris or London, which are typically less than 30 meters deep. The tunnel's diameter is also impressive, stretching up to 6 meters across, capable of handling an immense 2.2 million cubic meters of wastewater daily, which is equivalent to 900 Olympic-sized swimming pools. The construction of Singapore's project was a technical challenge, involving the use of slurry shield tunnel boring machines to navigate through the varied geology of Singapore from hard granite to soft marine clay. The project cost was approximately $2.7 billion, reflecting both its scale and complexity. A distinctive feature of the project is its integration with a comprehensive water recycling plan, where treated water is reclaimed and then purified further through advanced membrane technologies to produce NeWater, Singapore's brand of high-grade reclaimed water. However, the project was not without its difficulties. During construction, there were challenges related to the variable underground conditions, which required adaptive strategies to prevent disruptions. Additionally, the deep tunnel construction near urban areas posed risks of ground settlement, demanding constant monitoring and precise adjustment of tunneling operations. With plans for Phase 2 underway, which will extend the tunnel by another 100 kilometers, the system will continue to be a cornerstone of Singapore's water management infrastructure.
It's time to investigate the Sidu River Bridge, located in China. This suspension bridge spans an incredible 4,000 feet and is one of the highest bridges in the world, with a deck that towers 1,627 feet above the river below. The bridge connects the cities of Yesengguan and Daziping, dramatically improving transportation across the mountainous region. The construction of the Sidu River Bridge was a formidable challenge due to the extreme heights and the rugged terrain. The project involved over 2,000 workers who utilized advanced engineering techniques and faced considerable risks to complete the bridge. The bridge's main cables, each made up of 127 high-strength steel wires, were installed using a novel method that involved rocket technology to stretch the pilot lines across the vast gorge. This innovative approach allowed for precise placement and tensioning of the cables, ensuring the bridge's stability and structural integrity. One of the critical engineering achievements was the construction of the bridge's massive towers, which rise 295 feet above the bridge deck. These towers were built using reinforced concrete and were designed to withstand significant seismic activity, given the region's susceptibility to earthquakes. The bridge deck, constructed using lightweight yet strong materials, is designed to handle both vehicular and pedestrian traffic. The deck's aerodynamic design helps to reduce wind resistance and ensure stability during high winds, which are common in the mountainous area. The construction team also implemented a comprehensive monitoring system to continuously assess the bridge's structural health and detect any potential issues in real time, ensuring long-term safety and reliability. The Sidu River Bridge has significantly reduced travel times between the two cities it connects, fostering economic growth and development in the region.
Traveling to Sweden next, it's time to look into one of the biggest mines in Europe. The Kiruna mine is not only the world's largest iron ore mine, but also one of its most profound, with operations extending up to 1,365 meters below the surface. This mine, which has been operational since 1898, annually produces over 35 million tons of iron ore, dwarfing smaller operations like the Iron Mountain Mine in California. Kiruna's expansive network covers an area of 174 square miles, making it larger than the well-known Carajás mine in Brazil. The mine's innovative use of automated drilling and haulage technology marks it as one of the most modernized mines globally. With over 310 miles of roads within the mine, Kiruna operates like an underground city. Its depth and scale necessitate a unique ventilation system capable of circulating approximately 1,200 cubic meters of air per second. The relocation of Kiruna's town due to mining-induced ground deformation is a distinctive aspect unmatched by any other mining project globally. This massive undertaking involves moving residential buildings and key infrastructures to a new site 3 kilometers east, ensuring the town's sustainability and the mine's expansion. The estimated cost of relocation tops €1 billion, highlighting the scale and economic impact of this project on the local community. The mine's strategic importance is underscored by its contribution to Sweden's economy, supplying over 90% of the iron ore produced in Europe. Our next underwater project is the only underwater research laboratory in the world, and it's called the Aquarius Reef Base, located in the United States. Anchored 62 feet or 19 meters below the surface near Key Largo, this remarkable facility offers scientists a unique, aquatic vantage point for studying marine biology, underwater physiology, and the impacts of climate change on coral reefs. Established in 1986, Aquarius has facilitated groundbreaking research by allowing researchers to live and work in the ocean's depths for extended periods. The 400-square-foot habitat is equipped with living quarters, laboratories, and communication systems, enabling teams to dive deeper into their research without the daily decompression requirements that limit bottom time for surface divers. Being the only underwater lab in operation, the Aquarius Reef Base exemplifies human ingenuity in pursuit of scientific knowledge, turning the ocean's alien environment into a classroom. While that tunnel might be long, it's time to visit a tunnel that's over 10 times as long. The Channel Tunnel, an engineering feat that bridged the UK and France beneath the English Channel, stands as a symbol of European unity and technological ambition. Completed in 1994 at a cost of £12 billion, this project was one of the most significant engineering projects of the 20th century. Spanning 50.45 kilometers, with 37.9 kilometers beneath the sea, the Channel Tunnel holds the record for the longest undersea portion of any tunnel in the world. The construction involved the use of 11 tunnel boring machines to carve through the chalk marl beneath the seabed. This Herculean task required unprecedented coordination between British and French construction teams. The tunnel comprises 3 separate tubes, 2 for rail traffic and a smaller service tunnel that acts as an emergency escape route. The use of precast concrete linings to reinforce the tunnel walls was a critical component of the construction strategy, ensuring the tunnel's durability and safety. Today, the Channel Tunnel is a vital link for commerce and travel between the UK and continental Europe, facilitating the seamless transit of millions of passengers and tons of freight annually. It's time to travel to China for the Zhongnanshan Tunnel. Opened in 2007, it spans an impressive 18 kilometers or 11 miles, making it one of the longest mountain tunnels globally. This dual-tube tunnel cuts through the heart of Zhongnan Mountain, reducing the travel time between Xi'an and Ankang from 4 hours to just under 2 hours. Excavating at depths of up to 1,640 feet beneath the mountain peaks, the tunnel presented unique geological challenges. The construction teams encountered a range of difficult conditions from soft rocks and high groundwater inflow to hazardous gas emissions, each requiring bespoke solutions. The project's cost was estimated at approximately $470 million. One of the unique aspects of the Zhongnanshan Tunnel is its ventilation system. Given the tunnel's length and depth, maintaining air quality was paramount. The system is a pioneering effort in China for long tunnels, involving large ventilation towers that extract air from the center of the tunnel, ensuring the safety and comfort of motorists. This contrasts sharply with many older tunnels where simpler and less effective ventilation systems were implemented. Construction of the tunnel also set benchmarks in environmental conservation. The project included comprehensive measures to prevent damage to the local ecosystem, including relocating certain plant species and creating artificial waterways to redirect water flows altered by construction. In the tunnel's early years, it experienced problems with water leakage and ice formation in winter, posing risks to traffic safety. These problems were addressed through the retrofitting of the drainage system and the installation of an ice warning and response system, which have been critical in minimizing accidents and maintaining clear passage during the winter months.
Next on our list is the Vasco da Gama Bridge in Portugal. Spanning an impressive 10 miles, this bridge is the longest in Europe, connecting the northern and southern parts of Lisbon across the Tagus River. Completed in 1998, the Vasco da Gama Bridge was constructed to alleviate the traffic congestion on the 25 de Abro Bridge and to support the growing urban sprawl. The project cost approximately $1 billion, reflecting its vast scale and the advanced engineering techniques required for its completion. The construction of the Vasco da Gama Bridge was a monumental task, involving over 3,000 workers at its peak. The bridge's design includes several key features to ensure stability and longevity, particularly its resistance to seismic activity. Given Lisbon's history with earthquakes, special care was taken to incorporate flexible expansion joints and robust pylons that can withstand significant ground movement. The central span of the bridge is supported by cable-stayed structures with towers reaching up to 492 feet high, providing the necessary clearance for maritime traffic below. One of the most challenging aspects of the construction was dealing with varying depths and tidal conditions of the Tagus River. The bridge's foundations are anchored deep into the riverbed, using steel and concrete piles, some of which extend more than 300 feet below the surface. This method ensures that the structure remains stable despite the dynamic water conditions. Additionally, the bridge features a series of viaducts and causeways designed to blend seamlessly into the surrounding landscape, minimizing the environmental impact. The bridge significantly reduces travel time between northern and southern regions of the country, facilitating commerce and daily commutes for thousands of residents.
But the next underwater project is going to be a lot more feasible. The Gibraltar Strait Tunnel seeks to connect Europe and Africa, specifically Spain to Morocco, through a 14-kilometer underwater rail tunnel. This endeavor not only aims to bridge two continents, but also to significantly enhance economic and cultural exchanges between them. The project, with an estimated cost that could exceed $20 billion, is a testament to the potential of modern engineering to overcome geographical barriers. Construction of such a tunnel presents formidable challenges, from the deep waters of the Strait of Gibraltar, with depths up to 900 meters, to the seismic activity in the region. The proposed tunnel would be among the world's longest underwater tunnels, dwarfing existing ones in both ambition and technical complexity. Engineers are considering innovative boring techniques and special materials to ensure the tunnel's integrity and safety, taking lessons from other underwater projects like the Channel Tunnel between France and the United Kingdom. The United States also has constructed some really impressive underwater megaprojects, such as the Chesapeake Bay Bridge-Tunnel, stretching over the waters of the Chesapeake Bay to connect Virginia's eastern shore with the mainland. Opened in 1964 and expanded over the years, this 23-mile marvel is not just a bridge, but a series of bridges, tunnels, and artificial islands. Constructed at a cost of approximately $200 million at its inception, with subsequent expansions adding to the investment, the Bay Tunnel stands as a testament to human ingenuity and overcoming geographical challenges. The structure includes two 1-mile tunnels that dive beneath the bay, allowing ships to pass unimpeded above, while miles of low-lying trestle bridges provide breathtaking views of the surrounding waters. The use of the bridge-tunnel combination was a pioneering approach, providing a direct, uninterrupted flow of traffic across the bay and demonstrating a harmonious blend of functionality and environmental sensitivity. Let's travel to Turkey for the first project, where the Marmara Rail Tunnel was launched back in 2013, linking the European and Asian parts of Istanbul. Spanning approximately 76.3 kilometers in total length, with 13.6 kilometers running under the sea, the Marmara project was developed with a budget of $4 billion. The construction of the Marmara Tunnel involved the deployment of some of the most advanced technologies and machinery in the field of civil engineering. A pivotal element of this project was the use of immersed tube tunnel technology, which involves the fabrication of tunnel sections on land, subsequently towed to the site, and meticulously lowered onto a prepared trench on the seabed. However, one of the most significant hurdles was the archaeological discoveries made during the excavation phases. Istanbul's rich history was laid bare as the project unearthed a treasure trove of historical artifacts, including Byzantine ships, which required meticulous archaeological examination. It's time to investigate an immense underground project in South Korea. Yulhon Tunnel, which is the deepest and longest double-track subway tunnel in the world, was completed in 2020 after extensive construction that began in 2011. The tunnel stretches a remarkable 50.3 kilometers, connecting the city of Uiwang with the town of Yulhon, and runs as deep as 50 meters underground at some points. The construction of the Yulhon Tunnel was a significant undertaking, costing approximately $1.2 billion. The tunnel's role in South Korea's transit infrastructure is pivotal. It facilitates the operation of trains traveling at speeds up to 110 kilometers per hour, which is expected to slash journey times between key South Korean cities by more than an hour. The tunnel's design and construction employed advanced tunnel boring machines and new Austrian tunneling methods, which are considered state-of-the-art in the field of tunnel construction. However, the construction of the Yulhon Tunnel was not without its challenges. The project faced significant engineering hurdles, including managing the immense water inflow and stabilizing the tunnel walls in sections with loose earth. In addition to technical challenges, the project also encountered regulatory hurdles. There were concerns about potential impacts on local ecosystems and water tables, which led to rigorous environmental assessments and the implementation of several mitigation measures to protect the surrounding environment. These efforts demonstrate the complex balancing act required to execute such a massive underground project while minimizing ecological disruption. Let's travel to the Netherlands next for one of the most impressive underwater projects on the list so far. The Western Scheldt Tunnel, completed in 2003 at a cost of approximately €750 million, is not just a passage but a lifeline, connecting the regions of Zeeuws-Vlaanderen and South Beveland, and significantly reducing travel time in the area. Spanning an impressive 6.6 kilometers, the Western Scheldt Tunnel holds the title of the longest tunnel in the Netherlands. Constructed using the immersed tube method, it consists of segments that were meticulously built on land and then submerged and connected beneath the Scheldt River. This construction approach required precision and innovation, including the use of GPS technology to ensure exact alignment of the tunnel sections. But Japan is arguably even better at constructing underwater tunnels because they constructed the much longer Seikan Tunnel. Stretching 54 kilometers with a staggering 23 kilometers lying under the seabed, it connects the islands of Honshu and Hokkaido, piercing through the Tsugaru Strait. Completed in 1988 after nearly 2 decades of construction, the tunnel resolves the overcoming of geographical isolation and enhances connectivity. With an overall cost of approximately $3.6 billion, the Seikan Tunnel's construction presented formidable hurdles, including dealing with the seismic volatility of the region.
Starting with mechanical systems rather than foundations, the new Commander Stadium, scheduled for completion in 2028, will feature a complex network of distributed HVAC units, substation vaults, and emergency backup systems arranged around a high-redundancy operations core. Unlike traditional central plant configurations, this stadium will utilize multiple mechanical mezzanines at various elevations, each linked by vertical chasers running through the structural cores. These shafts will carry chilled water piping, variable air volume ducts, electrical busways, and fiber optic trunk lines. Heat and ventilation loads are carefully modeled for Washington's humid summers and cooler winters, and the stadium will incorporate both active and passive conditioning strategies, including thermally broken curtain wall assemblies and reflective rooftop surfaces. The foundation system is planned around a combination of driven precast, concrete piles, and drilled shafts, determined by subsurface variability across the large urban site. Prior to deep foundation work, the project team will need to execute extensive ground densification, as portions of the site lie in geologically loose soil conditions with historical fill. Where underground utilities intersect with the structural grid, pile caps will be reconfigured with built-in blockouts and ducts, enabling uninterrupted service routes. As the structural frame takes shape, the stadium will begin rising through a combination of cast-in-place concrete and structural steel. Core walls housing stairwells and elevators will be slip-formed in vertical stages, allowing reinforcement and embedded items to be installed continuously. Around these cores, steel raker beams will support precast seating elements, which are manufactured off-site and delivered in just-in-time deliveries. Each seating module includes cast-in embeds for railing systems, electrical conduit, and mounting brackets for digital displays. The stadium's exterior will feature a hybrid cladding system with aluminum composite panels, glazed sections, and ventilated rain screens. A unique vertical louver system will provide both shading and a dynamic visual profile that changes depending on the viewer's angle. These louvers are to be attached to a secondary steel frame mounted onto the primary structure using thermally isolated clips to prevent cold bridging. LED lighting strips and dynamic signage will be integrated into the facade, creating a programmable canvas for team branding and event-specific visuals. Above the bowl, a lightweight roof canopy is to be suspended from a cable-supported compression ring, offering broad shelter without enclosing the stadium. The structure relies on massive masts around the perimeter, each post tensioned into deep caissons. The roof surface itself will be constructed using a layered ETFE system with fritted coatings to control daylight penetration. Integrated gutters and scuppers will route stormwater to perimeter cisterns designed for reuse in irrigation and maintenance. Beneath the playing field, an array of hydronic tubing, drainage aggregate, and geofoam layers will create a fully conditioned surface that can withstand year-round use. Perimeter tunnels will provide access for maintenance and security personnel, while utility trenches will house lighting control lines, camera cabling, and telecommunications networks. For the Rio Grande LNG Train 4 expansion, work begins with an expansion plan that integrates seamlessly into the existing LNG facility's footprint while preserving safe operational distances between high-pressure equipment, storage tanks, and process lines. Civil engineering teams start by clearing and grading the designated construction pad, ensuring that the soil can bear the immense weight of cryogenic process modules and auxiliary systems. In this Gulf Coast environment, deep foundation piling is often required, with driven steel or precast concrete piles installed to reach stable strata below layers of soft, saturated soil. Once the ground improvements are complete, crews set out the anchor bolt patterns for the heavy process equipment foundations. Each foundation is a precisely engineered, reinforced concrete block designed to resist not just static weight, but also dynamic forces from machinery vibrations. Underground utilities, including cryogenic piping corridors, electrical conduits, and stormwater drainage, are laid early to avoid future excavation near high-risk areas. The core of Train 4's expansion revolves around its liquefaction process modules. These modules, typically prefabricated in large sections off-site, arrive via heavy lift transporters and are set in place using high-capacity crawler cranes. The arrangement includes gas pre-treatment units to remove CO2, H2S, and water vapor, followed by the main cryogenic heat exchangers and refrigeration compressor trains. These components operate under extremely low temperatures, so all associated piping is fitted with multi-layer insulation systems, vapor barriers, and stainless steel or aluminum cladding to prevent ice buildup and energy losses. Interconnection with the existing plant requires tie-ins to common utilities such as cooling water, nitrogen, instrument air, and flare systems. These tie-ins are executed during carefully scheduled outages or low load periods to minimize disruption to ongoing LNG production. High-pressure piping spools are hydro-tested to verify integrity before being connected, and every weld undergoes radiographic inspection for quality assurance. Electrical and control systems for Train 4 are integrated into the plant's distributed control system. Cable trays are installed on multi-tier racks, and miles of control and power cabling are pulled, terminated, and tested. Motor control centers, variable frequency drives for compressor motors, and backup generator systems are positioned within blast-resistant buildings to ensure operational continuity in case of an incident. Safety instrumented systems, including emergency shutdown valves, fire and gas detection sensors, and deluge systems, are calibrated and tested extensively before commissioning. Storage and loading infrastructure is evaluated to confirm that the expanded capacity can be accommodated. This may involve adding new LNG storage tanks or upgrading loading arms and pumps at the marine berth. LNG storage tanks are constructed with inner nickel steel shells and outer concrete shells, with polite insulation filling the annular space to maintain cryogenic temperatures. Set amid the subtropical lowlands of Central Florida, the construction of the Walt Disney World Resort in Orlando represented a pioneering feat of engineering, site development, and logistics management on an unprecedented scale. Spanning over 40 square miles, the transformation of this expansive and largely undeveloped land into a fully functional entertainment and hospitality complex required not only creative vision, but also advanced technical planning across multiple disciplines, including civil engineering, structural systems, utilities, transportation, and geotechnical stabilization. The first major task undertaken was the extensive site preparation, as much of the land was composed of wetlands, swamplands, and pine flatwoods with limited load-bearing capacity. To make the site suitable for large-scale construction, engineers employed a vast drainage and land reclamation strategy. A series of canals, retention basins, and stormwater management systems were excavated to control the water table and direct excess runoff into purpose-built bodies like Bay Lake and the Seven Seas Lagoon. This required dredging operations, the installation of culverts, and the construction of pump stations to regulate flow in both flood and drought conditions. Foundational work across the resort faced challenges due to the high water table and soft underlying soils. To ensure structural stability, deep foundations such as driven concrete piles and auger cast piles were commonly used, especially beneath heavy buildings like resort hotels and amusement park infrastructure. For lighter structures, engineers used preloading and surcharging techniques to compact the subgrade. In certain areas, soil cement stabilization and geotextile reinforcement were added to increase load distribution and prevent long-term settlement. Perhaps the most iconic aspect of the site's infrastructure was the creation of the so-called utilidor system beneath the Magic Kingdom. Rather than being true underground tunnels, these service corridors were constructed at the original ground level. The rest of the park was then built atop a massive earthen berm created by the spoil from the lagoon dredging. These utilidors house all the park's essential support systems, including electrical cabling, water distribution lines, HVAC systems, waste disposal, and logistics corridors, allowing for seamless and invisible operations above. Utility infrastructure was designed with redundancy and scale in mind. Independent water treatment and wastewater facilities were constructed on-site to handle the large demand. Extensive power distribution networks, including multiple substations, were integrated into the landscape to provide uninterrupted electrical supply across the property. Chilled water systems were installed to provide air conditioning via underground piping loops, using centralized plants that optimize energy efficiency. Transportation planning also played a critical role. A multimodal network was engineered to facilitate the movement of guests and goods, including monorail lines, ferryboat systems, internal bus loops, and service roadways. The monorail system, composed of elevated precast concrete beams supported by reinforced concrete piers, was built with precise tolerances to ensure smooth travel and high passenger throughput. All stations and transfer points were constructed with ADA, compliance and capacity planning in mind, utilizing modular concrete platforms, steel framing, and covered walkways. The scale and complexity of building the Walt Disney World Resort in Orlando set new benchmarks for themed development and remains a masterclass in how multidisciplinary engineering can be applied to create not just buildings or rides, but an entire controlled and immersive built environment engineered to handle millions of visitors each year with both efficiency and spectacle. Rather than focusing first on steel or foundations, the new Highmark Stadium, anticipated for completion in 2026, will distinguish itself through its climate-adapted design, shaped heavily by Buffalo's lake effect weather patterns and winter wind exposure. The entire project will be engineered with cold performance in mind, incorporating windbreak barriers, thermal zones, and strategically placed radiant heating elements throughout concourses, seating zones, and critical access points. Construction begins with site stabilization, which is critical due to historical fill and the seasonal freeze-thaw cycles in western New York. The earthwork scope includes excavation down to undisturbed subgrade, followed by layered backfill compacted in lifts. Foundations are primarily comprised of drilled shafts and reinforced concrete-grade beams, forming a grid beneath the stadium's structural core. Below-grade waterproofing membranes and under-drain systems are installed early to protect foundation elements from groundwater intrusion and ensure long-term durability. As superstructure work proceeds, cast-in-place cores rise first. These serve not only as the vertical circulation routes for fans, but also house major MEP infrastructure, fireproof stairwells, and elevator banks. Around these, a structural steel frame is erected using crawler cranes and modular steel assemblies. The framing system supports two major seating tiers, with mid-bowl premium areas cantilevered to preserve unobstructed sightlines. Seating decks are constructed using precast treads and risers with integrated embeds for power, data, and safety railing systems. The partial roof canopy, covering roughly 2/3 of the spectator seating, will be assembled from large truss girders supported by perimeter columns drilled into reinforced caisson foundations. The trusses will extend inward and upward to support a lightweight roofing material made of tensioned PTFE or ETFE, allowing snow to slide off and sunlight to penetrate. Gutter systems along the edge of the canopy will direct meltwater to a network of heated downspouts connected to storm retention tanks. These tanks will be buried below the main entry plazas and will double as part of the site's sustainable stormwater strategy. MEP systems are distributed through a dual-zone layout, one handling fan-facing infrastructure such as restrooms, concessions, and suites, and the other servicing field operations, security, broadcast control, and food service logistics. The HVAC system uses rooftop air handlers with glycol loops and distributed VAV boxes. Energy efficiency is achieved through economizer controls, occupancy sensors, and energy recovery ventilation. All critical systems are backed by on-site diesel generators housed in hardened enclosures designed to withstand blizzard-level wind and snow loading. The playing field itself will be composed of a hybrid grass system layered above a heated concrete slab. This slab contains embedded tubing for hydronic field heating, which keeps the root zone warm even in sub-zero temperatures. Above that, laser-graded sand and organic root media support the grass surface, with perimeter trenches and high-speed pumps managing surface runoff. Access tunnels will allow maintenance vehicles and television equipment to move below the seating bowl without disrupting game day operations. For a highway project like the Music City Loop in Nashville, the starting point is always the land acquisition and right-of-way preparation, which determines how the alignment will weave through existing terrain, neighborhoods, and commercial zones. Survey teams first establish precise control points along the proposed corridor, mapping every contour, property boundary, and existing utility line. This is crucial because a loop system must integrate with multiple interstate connections and arterial roads, requiring interchange designs that balance traffic flow with structural feasibility. Earthwork operations follow swiftly. Large bulldozers and excavators strip the topsoil and begin the cut and fill process, where high ground is lowered and low ground is raised to create the desired grade. In areas with soft clay or alluvial deposits, engineers implement soil stabilization techniques such as lime or cement treatment to improve bearing capacity. Where the loop crosses floodplains near river channels, elevated embankments or viaduct structures are introduced to maintain year-round access and protect against inundation. Bridges and overpasses become major focal points in a project of this scale. Concrete girder bridges are common, with precast elements fabricated at a yard and trucked to the site. Each girder is lifted into place with cranes, set on reinforced concrete piers and abutments that are themselves anchored into drilled shafts or driven piles. The deck is then formed, poured, and cured, after which barriers, lighting, and expansion joints are installed. Interchanges may require multi-level flyovers, demanding complex formwork systems and stage construction to maintain partial traffic movement during the build. Pavement construction is handled in a phased manner. The prepared subgrade receives a layer of granular base, compacted to exact density targets, followed by an asphalt binder course, or, in high-load sections, a continuously reinforced concrete pavement. For the loop's heaviest traffic zones, particularly where freight corridors converge, thicker pavement designs are used to accommodate decades of truck traffic without structural failure. Stringent quality control testing on material gradation, asphalt mix temperature, and concrete slump is conducted daily. Drainage infrastructure runs in parallel with the roadbed work. Culverts, storm sewers, and retention basins are placed to control runoff, and in urban approaches, curb and gutter systems with underground piping route stormwater into municipal systems. Because Nashville's topography includes rolling hills and sudden elevation changes, slope stability measures such as retaining walls, riprap armoring, and geotextile reinforcements are integrated into the design. Signage, guardrails, lighting, and intelligent transportation systems form the final operational layer. The ITS components, including traffic cameras, variable message boards, and ramp metering signals, are wired into a centralized control hub that can monitor congestion, detect incidents, and adjust lane use or ramp flow in real time. Noise barriers are installed where the loop borders residential areas, designed with absorptive panels to reduce highway sound levels. Throughout the construction process, coordination with utility companies ensures the relocation of water mains, gas lines, fiber optic cables, and electrical transmission lines without halting progress. Staging and sequencing are meticulously planned so that bridge crews, paving crews, and utility contractors can work in overlapping zones without interfering with one another. Beneath the waters and roadways of Miami, the Port Miami Deep Dredge and Tunnel projects reshaped both the marine and terrestrial access to one of the busiest cargo and cruise ports in the United States. These two interconnected mega projects required cutting-edge marine engineering, precision tunneling beneath a densely populated urban core, and rigorous coordination between federal, state, and local agencies to expand the port's capacity and streamline its logistics network. The Deep Dredge project aimed to deepen the port's main shipping channel from 42 feet to 50 feet, allowing for the accommodation of new Panamax-class vessels transiting through the expanded Panama Canal. To execute this, specialized dredging vessels were brought in, including cutter suction dredgers and trailing suction hopper dredgers, capable of removing millions of cubic yards of seabed material. The challenge lay not only in excavating to such depths, but doing so without disrupting sensitive marine habitats, port operations, or submerged utilities. Dredging operations were sequenced in phases, beginning with hydrographic surveys to precisely map the underwater topography. Blasting was employed in sections of dense limestone, with marine-safe explosives timed to avoid impact to sea life. The excavated material was carefully monitored and disposed of at authorized ocean disposal sites or used in beneficial reuse programs like beach renourishment. Environmental control measures included turbidity curtains and marine species observers aboard all vessels. Simultaneously, the Port Miami Tunnel project unfolded beneath Biscayne Bay. This initiative involved the construction of twin tubes running approximately 4,000 feet in length, connecting the MacArthur Causeway on Watson Island to Dodge Island, the heart of the port. The tunnels were designed to divert truck traffic from downtown Miami, enhancing safety and easing congestion. To construct these tunnels, a custom-built tunnel boring machine, nicknamed Harriet, was deployed. Weighing over 2,000 tons and spanning nearly 40 feet in diameter, the TBM was assembled in a launch pit on Watson Island and advance through a limestone substrate beneath the bay. The tunneling process involved simultaneous excavation and installation of precast concrete segment rings, forming the tunnel lining. These segments were waterproofed and grouted in place, forming a watertight shell that could withstand hydrostatic pressures and resist intrusion from saline water. Tunneling beneath the bay demanded constant monitoring of groundwater pressure, cut-ahead torque, and soil composition. The TBM operated with an earth pressure balance system to stabilize the tunnel face and prevent collapse. The spoil removed from the tunnel was conveyed by belt system to the launch shaft and trucked off-site. Crews worked in rotating shifts, operating around the clock to maintain excavation rates and minimize disruption to the bay and surrounding infrastructure. Once the structural shell was completed, interior systems were installed, including ventilation fans, LED lighting, fire suppression systems, CCTV surveillance, and emergency egress walkways. A robust stormwater drainage system was also built into the tunnel floor to channel any water intrusion into sump pits and eject it via high-capacity pumps. Taken together, the Port Miami Deep Dredge and tunnel projects not only increased the capacity and efficiency of port operations, but demonstrated how complex marine and tunneling engineering solutions can be successfully executed in a high-stakes, environmentally sensitive, and logistically intense urban setting. Beginning with vertical transportation systems, the new Everbank Stadium, projected for completion in 2028, will integrate an expanded array of elevators, escalators, and accessible ramps that are designed around a radial grid structure. Each of the stadium's core towers will house multiple vertical circulation shafts embedded into reinforced concrete shear walls that also provide the lateral stiffness necessary to withstand hurricane-level wind events common to Florida. These towers will not only support fan movement across multiple levels, but also serve as service corridors for mechanical systems, egress stairs, and emergency response paths. Descending to the foundations, the stadium will be built atop a substructure that accounts for both soft coastal soils and proximity to the St. Johns River. Engineers will employ a pile-supported mat foundation, combining steel H-piles driven to refusal with cast-in-place concrete caps and a continuous grade beam network. This system distributes both dead and live loads from the stadium's structure, while minimizing differential settlement across the wide footprint. Prior to foundation work, a ground improvement program involving surcharge loading and wick drains will be executed to consolidate moisture-laden soils and speed up the settlement curve. As the main seeding bowl is constructed, precast concrete modules will be staged off-site and delivered in sequenced shipments to be lifted by tower cranes into steel raker beams. These rakers will be bolted to cast-in-place support walls with embedded anchor plates and tensioned bolts. Each seating section will include cast-in penetrations for MEP stub-outs, lighting, and railing systems, reducing the need for secondary coring post-installation. The upper deck, designed to cantilever over the lower levels without obstructing views, will rest on long-span trusses that extend inward from perimeter support columns anchored in massive pier footings. Overhead, the partial canopy will be built from a network of curved steel girders arranged in an outward-leaning ring supported by inclined columns. The roof surface will feature tensioned PTFE fabric panels treated for UV and rain resistance, allowing diffused daylight while shielding fans from the elements. Integrated into the roof's edge will be high-capacity gutter systems and downspouts connected to underground stormwater retention tanks sized to accommodate peak rainfall events, typical to Jacksonville's climate. Mechanical and electrical systems will be divided into north and south zones, each with dedicated plant rooms housing chillers, air handlers, switchgear, and backup generators. HVAC supply and return will be routed through steel-framed duct risers, while electrical conduit will follow parallel chasers with thermal isolation to prevent overheating. Data infrastructure will be supported by multiple MDF and IDF rooms, each linked by redundant fiber lines to ensure seamless connectivity during events. The field system will incorporate natural Bermuda grass underlain by a heated subslab and vacuum drainage matrix. Below the root zone, temperature sensors and moisture probes will feed into a digital control system that adjusts irrigation and heating to maintain optimal growing conditions. The field perimeter will include recessed broadcast cable trays, camera mounts, and access ports for maintenance vehicles. With an official stadium opening targeted for the 2028 NFL season, final systems commissioning and occupancy certification are expected to wrap up in late summer of that year. Upon completion, the new Everbank Stadium will not only replace its predecessor, but redefine how an open-air venue performs in a subtropical urban environment. Work on the Chicago South Side Transit expansion starts with the mapping and alignment process, where planners determine how the new route will integrate into the existing rail network while minimizing displacement and disruption to the dense urban fabric. Surveyors conduct detailed, topographic, and structural assessments along the proposed corridor, documenting existing utilities, bridge clearances, and track geometries. Because this expansion is intended to connect neighborhoods more directly to the downtown core, special attention is given to designing stations and track alignments that fit into narrow rights of way without compromising operational speed. The first physical work often involves utility relocation. Water mains, sewer lines, and underground electrical conduits are moved to clear the way for track foundations and station structures. In many Southside neighborhoods, these utilities are decades old, requiring replacement rather than simple relocation. Crews coordinate closely with utility companies to stage these moves so they do not disrupt service to residents and businesses. Trackbed construction is one of the core elements. For elevated sections, new steel or concrete piers are installed, often by drilling deep shafts into the ground and pouring reinforced concrete to anchor them securely. Precast guideway beams or steel girders are then set atop these supports, forming the structure on which track will be laid. For at-grade or trenched sections, subgrade preparation involves excavation, placement of a granular base, and installation of drainage systems to keep water from undermining the ballast. Stations along the expansion route are designed with high platforms for level boarding, compliant with ADA requirements. The structural work for each station typically includes reinforced concrete slabs, steel framing for the canopies, and glazing for wind and weather protection. Passenger amenities, from seating to digital arrival boards, are integrated during later fit-out phases. Where possible, station designs incorporate community-focused elements such as retail kiosks, bike storage, and public art installations. Rail systems installation proceeds in parallel. Continuous welded rail is delivered in long sections, lifted onto the guideway and clipped to concrete or timber ties. Power delivery systems are built out, whether through an overhead catenary or third rail configuration, with all cabling routed through protected conduits. Signal systems, including automatic train control and communications-based train control, are mounted and tested to allow for high-frequency, safe operations once service begins. Bridges and overpasses form an important part of the build where the expansion must cross major roads, waterways, or existing rail lines. These are often prefabricated off-site and brought in for rapid installation, reducing the need for extended road closures. In dense traffic areas, night and weekend work windows are used to minimize the impact on commuters and freight traffic. Once the physical infrastructure is in place, the testing phase begins. This includes running test trains at various speeds to verify track geometry, braking distances, and signal responsiveness. Electrical systems are load tested, station facilities are checked for operational readiness, and emergency procedures are rehearsed. Instead of beginning with earthwork or steel, it's the structural interface between public concourses and premium zones that will stand out as a complex undertaking in the new Chicago Bears Stadium, which is planned for completion in 2027. Designed to be a multi-tiered facility with broad circulation paths and dedicated vertical access cores, the stadium will employ a tiered structural scheme to separate general admission, club level, and suite access into distinct vertical zones. This requires a dense network of stairwells, escalators, and elevators, all stacked in alignment with structural walls that also serve as lateral shear components. Moving down to the field level, the playing surface will be built on a multi-layered engineered base. A compacted subgrade of aggregate material will be topped by a network of subsurface drainage pipes laid in herringbone pattern. Above this, heating coils will be embedded in a concrete slab to provide winter conditioning, followed by engineered sand layers and the natural grass root zone. The perimeter includes trench drains and access vaults to manage both water removal and field utility service points. The stadium will feature a continuous seating bowl built from precast components tied into a poured-in-place concrete frame. The lower bowl will nest into the grade with retaining walls constructed early in the sequencing, allowing the earth to resist lateral loads and form a thermal mass. Above this, a steel-framed superstructure will support mid-bowl and upper-tier seating. Raker beams and cross-bracing will provide load transfer into deep foundations, which consist of drilled caissons extending to bedrock depths, necessary to combat frost heave and soil variability. Rather than building out roof structures at the final stage, this project will prioritize the canopy system earlier than typical. This is due to the use of integrated trusses that tie into upper concourse slabs, making the canopy part of the building's lateral stability system. It will consist of long-span steel trusses prefabricated off-site and craned into position using tandem lifts. Purlins and decking will support a roof skin composed of polycarbonate panels with integrated solar collection cells, adding resilience and contributing to energy offset goals. Mechanical systems will be distributed through mechanical mezzanines located between the upper decks and suite levels. Variable air volume units, hot water heating loops, and chilled beams will condition enclosed interior spaces. Open air concourses will be supported by displacement ventilation in enclosed service areas and radiant heating panels positioned under overhangs. Electrical infrastructure includes a central substation feeding redundant switchgear with additional UPS units designated for mission-critical systems such as lighting controls, security networks, and the scoreboard array. The exterior of the stadium will blend glass curtain walls, steel cladding, and stone masonry. Materials selected to echo both the historic civic buildings of Chicago and the city's modern architectural identity. A pedestrian plaza with integrated snow melt tubing will surround the stadium, channeling foot traffic through access-controlled entry gates aligned with structural grid lines. With all systems scheduled for commissioning by the second quarter of 2027, final testing, inspection, and certification will pave the way for the Bears to open their new stadium that fall, fully compliant with NFL standards and poised for multi-use flexibility in future decades. In the case of the Nashville International Airport New Horizon expansion, the work unfolds as a multi-phase effort designed to keep the airport fully operational, while substantially increasing capacity and modernizing its infrastructure. Initial activity begins with airfield and terminal area surveying, establishing precise reference points so that new construction ties seamlessly into existing taxiways, runways, and concourses. Given the tight geometry of active airside zones, staging areas for materials and equipment are carefully designated to avoid conflicts with aircraft movements and ground service operations. Earthwork and foundation operations for the terminal expansion start almost immediately after site clearance. Excavation crews remove unsuitable soils and place engineered fill, followed by deep foundation piling in areas where heavy superstructures such as multi-level concourses will rise. Concrete pile caps and grade beams are then cast to distribute loads from the terminal building's steel frame. Underground utilities are routed early in the process, including storm drainage systems, fuel hydrant lines, and large diameter chilled water piping for HVAC service. Structural steel erection is one of the most visible milestones. Steel columns and long-span roof trusses are lifted into position using crawler cranes, with connection bolts tightened to specification and every weld inspected. The roof structure for expanded gate areas must accommodate wide, column-free spans to allow unobstructed passenger circulation and clear sightlines to aircraft parking positions. Once the primary frame is complete, crews begin installing metal decking, followed by concrete slabs for the upper floors. Simultaneously, the terminal facade takes shape with curtain wall systems composed of insulated glass panels and aluminum framing. These assemblies are designed to maximize daylighting while meeting stringent acoustic requirements to reduce aircraft noise inside the building. Roof systems integrate both conventional weatherproofing membranes and provisions for photovoltaic panels in select zones. Interior build-out progresses in carefully coordinated stages. Mechanical systems are installed overhead, including large air handling units, ductwork, and high-efficiency chillers and boilers housed in mechanical penthouses. Electrical teams run conduit and pull wiring for lighting, communications, and security systems, ensuring redundancy for critical airport operations. Finishes follow: terrazzo flooring in high-traffic public zones, acoustical ceilings in passenger seating areas, and durable wall panels designed for ease of maintenance. One of the expansion's defining features is the upgrade to passenger processing areas. Baggage handling systems are expanded with high-speed conveyors, inline TSA screening stations, and integrated RFID tracking. Check-in halls are reconfigured for self-service kiosks and biometric boarding gates, all linked to the airport's IT backbone. Wayfinding signage and dynamic display boards are added to guide passengers efficiently through the expanded facility. Airside improvements are equally critical. New and reconfigured aircraft gates require concrete apron paving designed to withstand repeated loads from large commercial jets. Jet bridges are installed and tested for compatibility with multiple aircraft types, while fuel and ground power systems are extended to serve the added stands. Lighting upgrades improve apron visibility for nighttime operations, and advanced docking guidance systems help position aircraft with precision. Anchored along the banks of the St. Johns River in downtown Jacksonville, the development of Riverfront Plaza required a deliberate fusion of civil engineering, landscape architecture, and waterfront resiliency planning. The site, once occupied by the old Jacksonville Landing Marketplace, was reimagined as a dynamic public space integrating structural components with flood mitigation strategies, all while maintaining connectivity to adjacent urban infrastructure. From a construction and engineering standpoint, this project represented a complex interplay between environmental restoration, soil stabilization, urban utility integration, and open space programming. The first stage of construction focused on complete site clearing and demolition of the former structures. This phase involved selective dismantling techniques to minimize dust and vibrations, as the site is located near active traffic corridors, office buildings, and riverwalk segments. Demolition debris was sorted and recycled as part of a broader sustainability mandate, and existing below-grade utilities were mapped, capped, or rerouted to prepare the site for redevelopment. With demolition complete, the site was surveyed in high resolution to inform the grading and drainage plans. Given its proximity to the river and its susceptibility to tidal fluctuations and storm surges, the grading plan called for subtle terracing and the integration of bioswales to manage stormwater naturally. Fill material was imported and compacted in lifts, each tested for density and moisture content to prevent future settlement. Geotextile membranes were installed between fill layers to enhance soil stability and prevent erosion along the river's edge. One of the central challenges of the Riverfront Plaza redevelopment was the construction of structural retaining elements and hardscape features capable of withstanding both pedestrian use and hydrodynamic forces. Reinforced concrete retaining walls were formed along the Riverwalk edge, designed with weep holes and sub-drain systems to relieve hydrostatic pressure. These walls were anchored into the subgrade with helical piles in areas with softer soils, ensuring long-term stability against the variable forces of tidal surge and river currents. The plaza itself was constructed using a combination of cast-in-place and precast concrete paving systems, arranged in geometric patterns and supported by a subbase of compacted aggregate and fine leveling sand. Embedded conduits and utility chasers were integrated beneath the hardscape to support lighting, irrigation, and security systems. Special attention was given to expansion joints and surface drainage in the plaza design, with trench drains and permeable surfaces used to quickly shed water and avoid pooling during heavy rains. To support programming flexibility, the site included several utility stub-outs and foundational footings for potential future vertical structures such as pavilions or public art installations. Electrical cabinets and water connections were recessed and weatherproofed, and fiber optic conduits were installed for surveillance and wireless communication infrastructure. Landscape elements, including native trees, shrubs, and grasses, were selected for salt tolerance and deep root structures to minimize wind throw during storms. Tree pits were designed with structural soils and root barriers to protect adjacent pavement. Lighting was provided through architectural-grade LED fixtures mounted on concrete bases or embedded in pathways for both aesthetic and functional illumination. Unlike traditional stadiums that often feature concentric ring designs, the new Nissan Stadium, slated for completion in 2027, relies on a sweeping, asymmetrical configuration that responds to both the topography of the site and the orientation of surrounding city infrastructure. Located along the east bank of the Cumberland River, the stadium's footprint had to be carefully integrated with adjacent roads, bridges, and floodplain zones, which dictated early-stage decisions in earthworks and utility planning. Before vertical construction could even begin, site crews carried out a multi-phase ground improvement process that included dynamic compaction, surcharge loading, and the installation of wick drains to accelerate settlement. Structural work begins with a deep foundation system of drilled shafts socketed into bedrock. These shafts support a vast network of grade beams and pile caps that distribute vertical loads from the seating bowl, club levels, and roof system. Unlike traditional column layouts, this stadium uses staggered grids and variable bay widths to accommodate multiple functions: open concourses, press decks, and premium seating tiers. Concrete work is executed in sequence, with forming systems tailored to curved walls and sloped decks. Tower cranes positioned along the stadium's perimeter lift formwork, rebar bundles, and pre-tied mesh into place with logistical precision. The steel superstructure, meanwhile, is assembled from massive box girders and diagonal bracing members that define the profile of the upper seating bowl and roof. Truss segments arrive in prefabricated units from regional steel fabricators and are assembled on temporary shoring towers before final welding and bolting. Some of the longest cantilever trusses extend more than 200 feet over the seating area to support the edge of the canopy roof. These trusses transfer loads to reinforced concrete cores that double as vertical circulation towers. MEP systems are routed through centralized distribution corridors. Primary HVAC units are suspended in mechanical penthouses built into the roof structure, with chilled water and air supply lines running through steel grating walkways and vertical shafts. Electrical rooms feature dual-feed switchgear to ensure uninterrupted power delivery, especially during nationally televised events. Thousands of linear feet of low-voltage conduit are embedded in the seating risers to support seat-integrated lighting, power, and data ports. The stadium's roof is a major architectural and engineering focal point. Constructed from a combination of structural steel, cable tension systems, and ETFE membrane panels, it provides weather protection to over 2/3 of the seating bowl while remaining open over the playing field. Drainage from the roof is managed through concealed scuppers and high-capacity downspouts that feed into an underground stormwater retention system. Roof erection requires hydraulic strand jacks, temporary falsework, and real-time surveying to ensure millimeter-level accuracy during the tensioning process. Interior finishes will be applied in a final phase that includes terrazzo concourse flooring, steel mesh guardrails, and modular wall systems for suites and hospitality areas. Fire protection systems include both wet pipe and pre-action sprinkler configurations, with standpipes running through all stairwells and cores. As 2027 approaches, commissioning teams will systematically test building systems, conduct life safety inspections, and finalize documentation for occupancy certification, ushering in the full operational readiness of the new Nissan Stadium. Work on the Hampton Roads Bridge-Tunnel expansion begins with one of the most critical early tasks in any marine tunnel project: creating the staging and assembly areas for the massive tunnel boring machine that will carve out the new immersed tube sections. In this case, engineers first established a large-scale construction platform on artificial fill, extending from the shoreline to provide space for equipment, materials, and prefabrication activities. This required precise dredging and placement of engineered stone bedding to resist scouring from the strong tidal currents of the Chesapeake Bay. The logistics here are challenging because the site sits in an active shipping channel, forcing contractors to coordinate vessel movements and keep the navigation lanes open at all times. Once the staging area was ready, attention shifted to the launch pit for the tunnel boring machine. This involved driving reinforced steel sheet piles deep into the seabed to create a watertight cofferdam, followed by controlled excavation down to the required depth. Inside this pit, a concrete cradle was constructed to support and align the TBM's shield during launch. Simultaneously, a similar receiving pit was prepared on the opposite island to ensure the boring process could conclude without risk of misalignment or water ingress. On the marine side, barges and cranes were mobilized to handle the delivery and installation of precast tunnel segments. Each segment, manufactured onshore under strict tolerances, was brought out and lowered into place by specialized lifting frames, then joined with gaskets and bolted connections to ensure a watertight seal. These operations often had to be timed to coincide with favorable tidal conditions and minimal wind to prevent lateral movement during placement. Above the waterline, expansion of the approach trestles and bridge spans was tackled. New steel girder spans were fabricated and barged in, then lifted into position using floating cranes capable of handling hundreds of tons. Deck panels, consisting of precast concrete units with embedded reinforcement, were set into place, post-tensioned, and topped with a high-performance asphalt overlay designed for heavy traffic and coastal weather resistance. Inside the tunnel, after excavation, workers installed precast segmental liners, each fitted with embedded waterproof membranes. As sections were completed, the annular space between the liner and the excavated ground was pressure grouted to provide stability and prevent settlement. Mechanical, electrical, and safety systems were installed in parallel. This included fire suppression piping, LED lighting arrays, jet fans for ventilation, and a fully integrated monitoring network capable of detecting structural movement, water infiltration, or hazardous gases. A major engineering hurdle throughout was maintaining traffic flow on the existing bridge tunnel. Temporary lane shifts, stage closures, and floating work zones were used to minimize disruption. The expansion also required reinforcing the existing island structures to support the new tunnel portals and approach roadways, which involved deep foundation piling driven through variable soils ranging from loose sands to dense clays. In the southeastern corridor of the United States, where infrastructure development often grapples with both dense urbanization and expansive wetlands, the construction of the Brightline high-speed rail line connecting Miami to Orlando represented a major engineering endeavor. This privately funded rail project was designed not only to introduce high-speed rail to Florida, but also to demonstrate the viability of higher-speed passenger rail service within existing and constrained right-of-way corridors. The execution of this project required a comprehensive integration of new track construction, upgrades to existing freight corridors, and the implementation of advanced signaling and safety systems. Initial site work commenced with a detailed geotechnical analysis of the entire corridor, which spanned over 200 miles. This included evaluating soil stability, drainage characteristics, and subsurface conditions, particularly through the swamp-prone regions of Central Florida. In areas where existing tracks were used, such as the Florida East Coast Railway corridor between Miami and Cocoa, crews had to reinforce subgrades, replace worn ballast, and realign curves to support sustained higher speeds. Track geometry was meticulously adjusted using specialized rail alignment equipment to ensure smooth transitions and compliance with Federal Railroad Administration safety criteria. For the new segment between Cocoa and Orlando, a greenfield corridor was constructed largely along the State Road 528 Expressway median. This presented its own suite of engineering challenges, notably the design and construction of elevated track sections and bridges over sensitive wetlands and stormwater retention zones. Precast concrete girder spans were transported and installed using massive mobile cranes to expedite assembly and minimize environmental impact. Track beds along this route were laid on compacted sub-ballast, topped with engineered ballast layers, ensuring long-term durability under the dynamic loads imposed by high-speed rail operations. The track system employed continuously welded rail, which was delivered in long segments to reduce the number of expansion joints and improve ride quality. Rail thermite welding teams were deployed to join these segments on site with strict quality control to ensure alignment and weld strength. Dual track configurations were introduced in several key sections to allow bi-directional travel and service flexibility, especially near the Orlando International Airport terminus. Stations were another significant component of the build. The Miami Central Station, integrated into downtown Miami, required a complex vertical design solution involving multi-level platforms, elevated passenger concourses, and integrated commercial development. Structural steel framing supported concrete deck slabs, and the entire facility was constructed above active roadways and in proximity to other mass transit systems, necessitating rigorous coordination and sequencing of construction activities. Advanced signaling and communication systems were installed throughout the corridor, including positive train control, to ensure operational safety at high speeds. Grade crossings along the route were upgraded with quad gate systems, median separators, and enhanced warning devices to reduce the risk of vehicle-train interactions. Along the newer segments, full-grade separation was implemented via underpasses or overpasses. Instead of focusing first on structural systems, it's important to begin with the environmental remediation required for the Inter-Miami Freedom Park Stadium, expected to be completed in 2025. The site, a former municipal golf course with underlying contamination concerns, will undergo a thorough cleanup process before any building activity begins. This includes soil excavation, chemical stabilization, and the installation of vapor mitigation membranes to prevent any residual volatile compounds from entering occupied structures. Groundwater monitoring wells will be deployed around the perimeter during construction to track subsurface conditions in real time. Once environmental controls are in place, the next priority is site grading and drainage. The flat topography of the area demands an engineered solution for water management. Subsurface drainage basins and bioswales will be constructed throughout the property to capture and filter stormwater, routing excess into retention tanks placed beneath parking zones and service roads. These tanks are designed to handle the high rainfall intensity common in South Florida, with integrated pumping stations tied to the city's stormwater infrastructure. Foundational systems will vary slightly across the site, depending on load intensity and soil characteristics. The stadium itself will rest on a mat foundation supported by auger cast piles driven to refusal, while adjacent commercial and recreational structures may use shallow spread footings. The stadium's structural frame will consist of a composite steel and concrete system. Concrete cores will rise first, housing the elevator shafts and egress stairs, while structural steel beams and trusses will connect to these vertical elements, forming the primary load-bearing skeleton. The seating bowl is designed as a single-tier configuration with a steep pitch to create an intimate matchday experience. Precast concrete elements, risers, steps, and vomitories will be fabricated off-site and trucked in for sequential installation. Steel rakers and lateral bracing will provide support and rigidity. Integrated into the precast components will be electrical conduit and anchor points for seat mounting, lighting, and wireless access points. Above the stands, a sweeping roof canopy will stretch over the majority of the spectator area, constructed from lightweight cantilevered trusses and covered with PTFE fabric. This canopy will serve both functional and aesthetic purposes, shielding fans from intense sun and tropical rain while contributing to the venue's architectural identity. Rainwater captured by the canopy will be channeled into edge-mounted gutters, then diverted into a reuse system to irrigate the stadium's landscaping. Replacing the chain of rocks bridge begins with one of the most intricate planning stages in river bridge engineering. Designing a structure that can be built in parallel with an existing crossing while maintaining navigational clearance for Mississippi River traffic. Survey crews first conduct hydrographic mapping of the river channel, charting depths, sediment patterns, and current velocities. This data informs the placement of piers, ensuring they rest on stable strata while minimizing interference with the river's navigation lanes. Because the Mississippi's flow and sediment load are constantly shifting, engineers must also anticipate future scour conditions and integrate protective measures into the foundation design. The foundation work starts with massive cofferdams or drilled shaft platforms, depending on the pier location. In deeper water, large steel caissons are floated into place, sunk to the riverbed, and filled with concrete to form the pier bases. Each pier is built up from reinforced concrete, with embedded anchor points for the steel superstructure. At the same time, temporary work trestles extend from the shore to give cranes and crews safe access over the water. This staging infrastructure must be robust enough to handle heavy steel girder lifts while withstanding the river's seasonal flooding and ice flows. The superstructure erection follows a highly choreographed sequence. Large structural steel sections are fabricated off-site, trucked or barged to the site, and then lifted into position using floating cranes capable of handling hundreds of tons. To reduce midstream lifting complexity, some spans are assembled on barges and floated into position before being jacked up onto their bearings. Each connection is made with precision-drilled bolt patterns and often supplemented with field welding. All steel receives multiple coats of protective paint to guard against corrosion in the river's humid and industrial environment. Approach spans and ramps tie the main bridge into the surrounding highway network. earthwork teams construct approach embankments using compacted granular fill with retaining walls where the grade changes abruptly. The deck construction involves placing stay-in-place forms or removable falsework, followed by pouring a high-strength concrete slab over the steel girders. Expansion joints and bearings are carefully installed to accommodate thermal movement, while drainage scuppers ensure rainwater is directed off the deck and away from structural steel. Because this is a replacement project, demolition of the old bridge becomes its own engineering challenge. The sequence is planned so that no debris falls into the navigation channel, often requiring controlled lowering of sections onto barges. In some cases, explosives are used to drop spans in a controlled manner onto prepared mats in the water, with immediate recovery of all material. Steel is salvaged and recycled, while concrete is processed for reuse as aggregate in other projects. Rising from the urban fabric of downtown Miami, the Miami World Center represents one of the largest and most complex mixed-use developments in the United States, combining residential towers, retail space, hospitality venues, and transportation infrastructure within a tightly confined and highly active metropolitan zone. From an engineering and construction perspective, this multi-block development introduced significant challenges in staging, subsurface coordination, and structural integration across disparate building types, all while maintaining operational continuity in one of Florida's busiest urban centers. Site preparation began with extensive demolition and clearing operations. Much of the project footprint was previously occupied by low-rise commercial buildings and underutilized parcels, which required systematic dismantling and remediation. Excavation crews were tasked with removing foundations, underground storage tanks, and legacy utilities while coordinating with the city to preserve or relocate critical service lines. Due to the high water table typical of coastal Miami, dewatering systems were installed early in the process using deep well points and submersible pumps to manage groundwater during foundation work. The structural design of the various towers and podiums involved a combination of reinforced concrete frames and post-tensioned slabs, tailored to meet both vertical load demands and lateral wind forces characteristic of hurricane-prone South Florida. High-rise residential components, some exceeding 50 stories, were supported by deep pile foundations driven into stable limestone strata. These piles were tested using static and dynamic load tests to confirm bearing capacity and settlement behavior prior to full-scale construction. To accommodate multiple uses within tight spatial constraints, engineers designed large podium structures that span entire blocks and house parking decks, retail space, mechanical rooms, and loading docks. These podiums utilized cast-in-place concrete cores and transfer slabs, with integrated fireproofing and acoustic treatments to separate commercial activities from the residential levels above. The coordination of vertical transportation systems, including high-capacity elevators, escalators, and stairwells, was managed using 3D building information modeling to avoid clashes and optimize flow. One of the most technically demanding aspects of the Miami World Center was its subterranean utility coordination. Given the density of existing municipal lines and the proximity to the Metro Rail and Brightline stations, all underground installations, ranging from electrical conduits to stormwater management systems, had to be precisely routed and sequenced. Redundant systems were designed for critical infrastructure, including dual water feeds and backup generators located above flood elevation in compliance with updated coastal resiliency codes. Facade systems for the towers included unitized curtain wall assemblies with insulated glazing and hurricane-resistant frames, assembled off-site and installed using tower cranes and specialized rigging teams. Balconies, a hallmark of Miami residential design, were cantilevered with post-tensioned slab extensions, requiring careful engineering to mitigate deflection and ensure long-term durability in the saline air environment. Finally, staging and logistics played a pivotal role throughout the multi-year construction schedule. With multiple general contractors operating simultaneously on adjacent parcels, vertical and horizontal movement of materials had to be tightly choreographed. Dedicated staging zones, off-site prefabrication yards, and synchronized crane operations minimized congestion and ensured safety across the development. Rather than beginning with infrastructure or shell work, the new Las Vegas Stadium, projected for completion in 2030, will start with the unique constraint of integrating into a tightly packed urban grid, adjacent to high-rise developments and hospitality venues. The pre-construction phase will involve extensive underground mapping, seismic zoning studies, and coordination with municipal transit systems. Because of the arid soil conditions and high potential for differential settlement, the site will undergo soil cement stabilization and the installation of moisture barriers before any structural excavation begins. The stadium's foundational system will rely on a dense grid of drilled piers extending deep into compacted desert substrata. These piers will support a post-tensioned concrete mat foundation designed to disperse vertical and lateral loads evenly across the uneven site. Embedded within this mat will be seismic base isolators, engineered to decouple the structure from ground movement in the event of an earthquake. Construction teams will stage equipment and materials using vertical lifts and a satellite laydown yard located several blocks away, minimizing disruption to nearby properties. Once below-grade systems are in place, vertical construction will begin with cast-in-place concrete cores that serve as the stadium's structural spines. Each of these cores will include fire-rated stairwells, elevator shafts, mechanical risers, and egress corridors. Simultaneously, the steel skeleton of the seating bowl will rise in a tiered sequence. Long-span trusses, fabricated off-site, will be lifted into position by lattice boom crawler cranes and temporarily braced using hydraulic shoring towers. These trusses will provide cantilevered support for luxury suites and upper-tier seating decks. The stadium's fully enclosed, climate-controlled roof will be a defining feature. Constructed from a combination of steel arches and a transparent ETFE membrane, the roof will span from end zone to end zone, supported by a pair of super trusses anchored into reinforced buttresses outside the main bowl. This roof will not only seal the stadium from the scorching desert climate, but also include operable louvers and shading fins that dynamically respond to solar intensity. A rooftop photovoltaic array will supplement the energy supply, integrated with a battery storage system located within a dedicated service vault. HVAC and power systems will be engineered to support the intense energy demands of a fully enclosed facility in the Mojave heat. Massive chilled water plants will operate on closed-loop systems, with thermal storage tanks allowing cooling operations to run during off-peak energy hours. Air distribution will utilize under-seat displacement vents in the seating areas and high-induction diffusers throughout the concourses. Electrical rooms will feature high-capacity switchgear, redundant transformers, and power conditioning systems to support lighting, broadcast, and emergency systems. The playing surface will be designed as a retractable, natural grass tray that can roll out onto an exterior service apron when not in use. This system allows the field to receive full sunlight and air circulation, preserving turf quality while minimizing indoor moisture accumulation. The rolling tray will glide on steel rails supported by hydraulic actuators and guided by laser sensors. By the final quarter of 2030, the stadium will be undergoing systems commissioning, staff onboarding, and final municipal inspections. The Las Vegas Stadium will then open its doors as one of the most technically advanced indoor venues in the world, tailored for year-round sporting and entertainment events in one of the most climate-challenging urban centers in North America. In the case of the Coastal Virginia Offshore Wind Project, the entire effort hinges on the careful coordination of marine construction in open ocean conditions, which demands a completely different approach than land-based renewable energy developments. The process begins long before any steel touches the water with an exhaustive geotechnical survey of the seabed. Crews deploy specialized survey vessels equipped with multi-beam sonar, sub-bottom profilers, and cone penetration testing equipment to map the subsurface layers in fine detail. This information dictates the exact placement and design of the turbine foundations, as the Atlantic sandy sediments can vary greatly in density and composition over relatively short distances. Once the optimal positions are confirmed, the installation phase for the foundations begins. Jack-up installation vessels, capable of lifting themselves out of the water on massive legs for stability, are mobilized to the site. Each turbine foundation, typically a monopile in this particular project scale, is fabricated onshore, transported by barge, and then driven deep into the seabed using hydraulic impact hammers. To prevent scouring around these foundations from constant wave and current action, a protective layer of rock armor is placed at the base, delivered by fall pipe vessels that can accurately drop stone in rough seas. Following the establishment of foundations, transition pieces are installed. These are cylindrical structures fitted over the top of the monopiles, designed to provide a precise connection interface for the turbine towers. Inside these transition pieces, workers fit ladders, cable hang-offs, and landing platforms for future maintenance access. All bolted connections are pre-tensioned to exact specifications, and every weld is inspected both visually and with non-destructive testing to ensure long-term durability in the harsh marine environment. Parallel to the structural work, cable laying operations take place. High voltage export cables, manufactured in continuous lengths, are loaded onto specialized cable laying vessels equipped with large turntables. From the offshore site to the onshore landing point, the cable is carefully placed into pre-dredged trenches and then buried using either jetting or plowing systems to protect it from anchors and fishing gear. Near shore, horizontal directional drilling is used to pull the cable through to a land-based transition station without disturbing the beach or nearshore ecosystem. The turbine assembly process is one of the most visually striking parts of the project. Tower sections, nacelles, and rotor blades are transported offshore and installed in a carefully choreographed sequence. Tower sections are lifted and bolted together first, followed by the placement of the nacelle, the housing for the generator and gearbox, and finally, the massive blades, each of which can be well over 100 meters in length. Given the limited weather windows for safe lifts, every component's arrival and installation is timed to the hour. Back on shore, the grid connection infrastructure is constructed. This includes the installation of transformers, switchgear, and protection systems to integrate the offshore generation into the regional power network. Once testing and commissioning are complete, the wind farm begins full operation, delivering clean energy while being monitored from an onshore control center that can track turbine performance, detect anomalies, and even adjust blade pitch remotely to maximize efficiency and minimize wear. Stretching across the southern portion of Florida, the Everglades represents one of the most unique and delicate ecosystems in North America, and the series of restoration projects aimed at rehabilitating this landscape stand as some of the most ambitious hydrological engineering efforts ever undertaken in the United States. These projects collectively focus on undoing decades of human alteration that disrupted natural water flows, severely impacted wildlife habitats, and degraded water quality. The engineering challenges associated with these efforts are vast, involving large-scale earth moving, hydrological modeling, structural water control features, and long-term adaptive management. At the heart of the restoration initiative is the re-establishment of natural sheet flow, which refers to the slow, shallow movement of water southward across the Everglades flat terrain. Historically, this flow was interrupted by the construction of levees, canals, and pumping stations that redirected water for urban and agricultural uses. To address this, engineers have designed and constructed massive flow equalization basins, stormwater treatment areas, and pump stations that carefully mimic the timing and volume of historical water deliveries. One of the key undertakings involved the removal or modification of hundreds of miles of canals and levees, such as the partial deconstruction of the Miami Canal and the rerouting of flow into restored wetland corridors. This work required precise excavation and reshaping of land to ensure that water could once again disperse evenly and slowly across the landscape. Earth-moving operations were executed with amphibious excavators and low ground pressure tracked vehicles to reduce soil compaction and environmental disruption. In areas where water storage was a major constraint, large reservoirs were constructed, some exceeding tens of thousands of acre-feet in capacity. These reservoirs are lined and equipped with high-volume inflow and outflow structures controlled by gated spillways and electrically operated valves. Their purpose is to capture stormwater during wet seasons and release it in a controlled manner during dry periods, mimicking natural hydrological cycles. Adjacent to these reservoirs are extensive stormwater treatment areas composed of shallow, vegetated cells that use aquatic plants like cattails and submerged vegetation to remove excess phosphorus and other nutrients. The restoration projects also necessitated the construction of extensive culvert networks and bridges to allow water to pass underneath roadways, particularly along major east-west transportation corridors such as Tamiami Trail. These structures were designed to accommodate large volumes of slow-moving water without impeding traffic or causing structural undermining. The foundations of these bridges were pile-driven deep into stable substrata, and the superstructures were built using pre-stressed concrete beams capable of withstanding Florida's corrosive and humid environment. Monitoring infrastructure is integrated throughout the system, including flow gauges, water quality sensors, and automated telemetry stations. Data collected from these devices feed into centralized control systems that allow engineers and hydrologists to make real-time adjustments to water releases, ensuring ecological targets are met. The adaptive management strategy also includes provisions for ongoing modifications as performance data accumulates over years of operation. Stretching through the heart of Central Florida, the I-4 Ultimate project in Orlando represented a massive reconstruction and modernization of one of the state's most heavily traveled interstate corridors. The scale of this infrastructure initiative, spanning 21 miles, required an extraordinary application of highway engineering, traffic management, and structural design, all executed under live traffic conditions. The goal was not merely to widen the interstate, but to reconfigure it entirely to improve traffic flow, safety, and long-term capacity, incorporating express toll lanes, new interchanges, and updated overpasses. The initial phase of work focused on utility relocation and right-of-way clearing, including the removal of outdated bridges, underpasses, and surface roads. Utility coordination was especially complex given the corridor's urban setting. High-voltage transmission lines, water mains, gas pipelines, and fiber optic conduits were identified, surveyed, and in many cases rerouted through newly constructed utility corridors. Horizontal directional drilling and jack and bore methods were used extensively to install new conduits beneath active roadways without disrupting surface traffic. One of the hallmark features of the project was the addition of 4 managed express lanes in the center of the existing interstate. To construct these, engineers had to widen the footprint of the corridor and build new median support structures while maintaining the existing traffic lanes. This required extensive temporary shoring, phased traffic shifts, and the use of movable barrier systems. The new lanes were constructed with concrete pavement sections over a stabilized subbase and geotextile reinforced subgrade to support long-term heavy vehicle use. Bridges were a major component of the reconstruction effort, with over 100 new or rebuilt bridges included in the project scope. These ranged from short-span box girder structures to complex multi-level flyover ramps. Precast concrete beams were fabricated off-site and delivered during off-peak hours to minimize traffic disruption. Each bridge's foundation system was engineered to match local soil conditions, typically involving driven steel H-piles or drilled shafts. Bearing pads, expansion joints, and shear connectors were meticulously installed to ensure long-term durability and thermal movement capacity. The project's interchanges were completely redesigned to eliminate weaving and improve vehicular throughput. One of the most complex interchanges was the one at State Road 408, which required stacking multiple levels of traffic lanes, supported by tall piers and connected through sweeping curved ramps. Special seismic joints and post-tensioning systems were used in some of these long-span ramps to meet structural integrity standards and allow for maintenance access. Intelligent transportation systems were integrated throughout the corridor, including overhead gantries with dynamic message signs, cameras, and electronic toll collection systems. The express lanes were outfitted with barrier separation and entry-exit gates, spaced strategically to manage congestion. All ITS components were wired into a centralized traffic operations center, allowing for real-time monitoring and incident response.